Okay, well, welcome to Reinforcement Learning for Information Retrieval. I hope everybody can hear me okay. We're a group of 5 researchers from Blue Prism AI Labs. We put this tutorial together. Yeah, we hope you enjoy it. So yeah, we're Alex, Miguel, myself, Dell and Murat. So the first thing to note really is we've got all the information that's relevant to the tutorials on this website. So if you need any, need to access the tutorials or find out information or look for quick links, that's the best place to go. rl-starterpack.github.io. Just first, quickly the schedule. So we're in the UK, so I'm afraid we like to do things a bit differently, and these are all times in BST. But we'll be kicking off now with reinforcement learning basics and tabular Q learning. So that'll be a presentation and an exercise. Then we'll start deep Q networks before we move into a coffee break, and we'll work through the rest of the syllabus in the rest of the day. We've extended the lunch break a little bit just to fit the schedule in. But what will happen is before the lunch break, we'll have one of the exercises. So if some of us can hang around and help with an extended exercise session, if that helps. So just how we like to keep things organized on Zoom while we're presenting. So if you can, keep yourself muted. Try not to share your screen. Obviously the chat is there to ask questions at any time. Hopefully the presenter will see them as they crop up. And then during the tutorial exercises, just feel free to use the audio or ask in the chat. You know, you can share your screen and we'll help as best we can at that point. And, you know, it's obviously good to keep background noise to a minimum. Okay, I'm going to hand over to Dell, who's going to introduce some motivation for why reinforcement learning for information retrieval.
Hi, good morning. This is Zhang from Blue Prism AI Labs. In recent years, we have all witnessed very rapid development and great successes of reinforcement learning, particularly when it is combined with deep learning. For example, the AlphaGo and many other successes done by DeepMind and also other companies in the AI field. So unsurprisingly, many information retrieval researchers and also practitioners have become very interested in applying reinforcement learning techniques to solve challenging information retrieval problems. For example, just in 2020, the term reinforcement learning has been mentioned more than 60 times in different papers published by ECIR. So actually, every time I check again, this number is growing because of more papers being indexed by Google Scholar. So essentially, in information retrieval, using reinforcement learning, we could go beyond the independence relevance assumption. So the retrieval problem could be formulated as a sequential decision-making problem. And we are going to discuss this later in our sessions about the applications of reinforcement learning to information retrieval problems, including search, recommendation, and advertising. The growing popularity of reinforcement learning in the field of IR is attributed not only to the technology push, but also the demand pool. So nowadays, more and more information retrieval applications would be delivered as web apps or mobile apps. So in these kind of new style IR systems, they have become much more personalized and much more interactive. So the traditional information retrieval approach that assume user preference being static and try to maximize the immediate user satisfaction would no longer work very well. So reinforcement learning is a perfect tool and a promising approach to tackling the problem of personalization as well as interactivity, because we could capture the user's evolving interests and try to optimize their long-term engagement. So it has been reported that many internet companies nowadays, like Google and Alibaba, they have started to gain competitive advantage from their reinforcement learning engines for search and recommendation and advertising. So I'm passing forward to Zhang.
Thank you, Dell. Yeah, okay, so let's kick off with reinforcement learning basics. Okay, right, so I mean, we just want to set the scene really and put reinforcement learning in context to start with. So these are the three main pillars of modern machine learning: supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, as you probably well know, we've got well-defined input and output data. So there's a teaching signal. So the right and the wrong are explicitly provided. Unsupervised learning is kind of the other end of the spectrum. So we've got well-defined data, we've got no teaching signal, however. There isn't really a right or a wrong. You're just trying to discover patterns in the data to try and understand what the data looks like. So reinforcement learning is different. We're trying to learn through interaction with the environment. So we assume there's some sort of, well, we're given an environment and there is some sort of reward signal. Right and wrong are provided implicitly through these rewards. Okay, so what is reinforcement learning? Well, you can summarize it in a few different ways, but at the end of the day, it's really about learning what to do. And this involves mapping situations or states to actions, whilst at the same time learning to maximize rewards. So the most basic form of RL involves an agent interacting with an environment. So the agent acts upon the environment updates its state according to the action and returns the updated state to the agent along with a reward signal. And this is an ongoing iterative process. Here we try to make some of these concepts we just discussed a little bit more explicit. So the agent is the thing that learns. The environment is the system that the agent interacts with. This could be a real world environment or a simulation in a computer. So when we say policy, we're talking about the agent's behavior. And this is what we want to update during learning. This itself could be stochastic or deterministic. The reward signal is what the environment provides to the agent to help them understand how well it is doing. And it's important to note that each reward is an immediate signal, localized in time. Typically, however, the agent's goal is to maximize its total reward in the long run. The value function specifies what is good in the long run. So given a state, what rewards the agent can expect to accumulate over time. And then the last piece here, the model of the environment. This is optional really, but it typically helps. And it offers, so if the agent has some understanding of how the environment works, it offers the agent the ability to plan. So it can make decisions based on how it expects the environment to react. Now, there's two forms of RL, model-based and model-free. So model-based is typically easier because you can do this planning and you understand the environment, at least to some extent. Whereas model-free is a more general form where you do not need to have any understanding of how the environment works. Okay, so those are the elements. What are the characteristics? So we're going to make these more explicit later on, but I think it makes sense just to run through them here. So first of all, there's almost always some degree of trial and error. So the agent typically starts with very little prior knowledge and therefore needs to experiment to discover what is good. Following that, there's exploration versus exploitation. You can see that trial and error is necessary to improve upon initial random policies. But what about once the agent has learned some level of good behavior? Should it continue to experiment to discover even better behavior? How much should it exploit the good behavior that it has already learned? Often there is a tension between these two goals and some sort of compromise must be reached. Delayed rewards. So quite often there is the difficulty of delayed rewards. It may not be obvious what value a state has until some time later. So the learning signal can be quite distant in time from when a good action must be chosen. And sparse rewards are often a cause of this difficulty. So sparse rewards occur in many environments, and these happen when the agent does not know how well it is doing until the end of the task. Okay, uncertain environment. So this can manifest in two ways. The agent may not have a good model of the environment, can be one thing. It may have no model of the environment, or indeed the environment itself may be stochastic and unpredictable. And this can obviously make the whole problem a lot more difficult. There's the consider whole problem characteristic. So quite often in supervised and unsupervised learning, you're using machine learning as part of a larger system. Whereas in reinforcement learning, you typically consider the whole problem to be solved and ask the agent to learn how to do that. And then finally, there's on and off policy. So there's also this distinction as to whether the agent uses data generated from its interaction with the environment, or if it uses data available from any source. On policy is normally to be preferred, where the agent learns from its own interactions with the environment. Off policy is the opposite, where the agent learns from data generated elsewhere. But obviously this can come with certain biases and assumptions underneath it. Okay, so most reinforcement learning systems can be put in the framework of Markov decision processes. So we have a cartoon here. The states are represented by the green S0, S1, and S2 nodes. The actions are represented by the orange, I guess, A0 and A1 nodes. When in any state, the agent can take one of two actions, A0 or A1. Given a state and an action, there are probabilities describing the likelihood of transition to subsequent states. So this is a discrete time stochastic control process. It's discrete time because we've got sequential interactions with the environment. It's stochastic because there's an uncertain environment, as evidenced by the probabilities. It's a control process because the agent is acting on the environment by choosing the actions. And it's Markov. The Markov assumption holds because we only need to know what the current state is. The history does not matter. This is normally a simplifying assumption, but we find it often works surprisingly well. And there's also this partially observability extension. So in a POMDP, the situation is a little bit more difficult because the agent is not aware which state it is in. Okay, so how does the agent interact with the environment? So I think we're just going to go through this in a little bit more detail now. So when presented with a state from the environment, the agent will sample an action A from its policy pi, which is itself a function of the state S. The agent will take the action A in the environment, resulting in a new state S t plus 1. And that is sampled from WS. So So these W represent the distributions that encapsulate the environment. At the same time, the environment also samples a reward from this WR distribution. Now, the agent will be updated with the new state and the new reward. It can decide how to update its policy pi, and the whole process can iterate. So as this process iterates, this results in rollouts, also known as episodes or trajectories. And these can be seen as sequences of state, action, reward tuples. So each time we go around the loop, we're getting this tuple of state, action, reward. And this trajectory tau can be of arbitrary length. So just going back to this model-free versus model-based. So if the agent has some awareness of these W distributions, we said is model-based. If it has no idea, then it's model-free. Okay, so really this credit assignment problem that we're going to talk about on this slide is at the heart of reinforcement learning. So it asks which actions led to the reward signal. And as we mentioned before, delayed and or sparse rewards can make this difficult. So trial and error is often required. And if we look a bit more closely at this diagram, we can see an example of this. So we see, here we see two rewards. So there's +5 here at the top in the transition from S1 to S0 via action A0. And there's a reward, a negative reward, a -1 in the transition from state 2 to state 0 via action A1. So here we really want the agent to learn that the action A1 in state S2, so sorry, the action here A1 in state S2 can be good despite this chance of the immediate negative reward. And we can see that because the only way to get to this large positive reward, +5, is via this action A1 taken from state S2. And that's when you traverse up to S1, you take action A0, and you come back to S0. So here we see that when in state S2, we need to learn to take action A1, but the reward itself is delayed. So here we have the credit assignment problem. How do we assign the credit to action A1 in state S2? Okay, rewards and returns. So we've spoken about rewards and we've spoken about value functions. So what's a return? So, well, the reward was a localized signal about how well the agent is doing, but the return is a similar signal averaged over time. So typically we phrase our reinforcement learning problem as an optimization of cumulative rewards in the long run. So an optimize to maximize the return we see. So on the left, we've got the rollout diagram that we had before. And on the right, we've got two types of returns. So for any episode tau, the return is defined as a weighted sum of the rewards. So on the top, we've got a infinite horizon discounted return. So we've got this gamma discounting factor. This will be between 0 and 1. And as we look further into the future, the effect of our rewards are going to get less and less because of this exponential term. We can also use a finite horizon, undiscounted return. So here we're just summing h steps into the future and using that as the object we'd like to maximize. Now you can combine these and you can have an infinite horizon undiscounted return. But in practice, these don't tend to work so well because the agents have got no incentive to discover a behavior that leads to rewards in the short term. They're just as happy if their behavior leads to a reward in the long run. So they can become lazy in some way. Okay, value-based methods. Well, maybe before we go on to value-based methods, I'll just ask, have we got any questions? Okay. Okay, so in this session, we're going to discuss, I mean, that's really the basics. So we'll go on to value-based methods and tabular Q learning now. So in this session, we're going to discuss value-based methods that estimate this value function. So there's other methods like policy gradient, and they're going to optimize the policy directly without estimating the value, but they're going to be in later sessions. So the value function describes the worth of being in a state or of being in a state and taking some action. So these are these V and Q functions respectively on the slide. So we can see here that they're expectations of returns, right? And they're conditional on a starting state S0. So the V function is saying, suppose we're in starting state S and we're using policy pi. What's our expected reward given all possible rollouts? And this expectation, you know, pi can be a stochastic policy, so there can be randomness there, but also the environment can be random. So this expectation is really over all of the stochasticity in the system. And then the Q value is exactly the same thing, but here we're just also conditioning on the action. So here we're saying, what's the value of taking action A when we're in state S? So we're conditioning that S0 is S and A0 is A. And it's exactly the same expectation, quantity, the reward, sorry, the return. Okay, so maybe it's easiest just to go through all of this with an example. This is a sort of starter reinforcement learning environment that we're going to experiment with. So there's a frozen lake, and you have unfortunately lost your frisbee on this lake. Even worse, the ice is slippery and movement on the lake is uncertain. So even if you want to go one way, you might end up going a different way. Also, there are holes in the lakes that you can fall into. Now, you could easily say, oh, well, it is only a frisbee. Maybe it's not worth going on the lake and falling in the holes and risking your life. But actually, there's an international frisbee shortage, and you must retrieve this disc. So in this grid, we can see the rewards for arriving at the terminal states. So we're going to start up here in the top left, and we're going to move across this lake. Now there's 4 holes where the rewards are -1, and our goal is to reach the frisbee at the bottom right, where the reward is +1. So our task is to learn how to navigate this lake from the start to the goal. Okay, so one way to use reinforcement learning to solve this problem is to estimate the value function. So here we would have estimates of the values of each state, and this would go some way to defining a policy to control navigation across the lake. So here we see some numbers given to each state, and they're illustrations of state values, this V function. And you can see that close to a hole, values tend to be smaller, and close to the goal, the values tend to be higher. So if our agent was aware of all of these, the values of all the states around it, it would be fairly straightforward to form a policy for which direction to travel in. So for example, if we're here at this state here, 0.4, and we knew 0.7 was down here, and all the other ones were lower, you know, it'd be reasonably easy to form a policy to ask to go down. However, we're going to make life a little bit more complicated for ourselves. So we're going to say we want a model-free agent, and that's really what tabular Q learning is going to give us. So this model-free setting, like we said before, is more general than model-based. So we're going to consider that. So here we're going to say we don't know anything about the environment. In particular, we don't know which state we're likely to end up in after taking a particular action. So say we're in this state here, and we wanted to choose an action to take. Well, we wouldn't know that going down would likely lead us to the state below. So even if we knew the value function for the state below, that wouldn't really help us. So this motivates Q learning. So you probably noticed that the value functions were called V and Q. So tabular Q learning is all about estimating the Q value function not the V. And this is a very general form of reinforcement learning, as it's model-free. And we're going to contrast that to a model-based reinforcement learning in the next slide. Yeah, so I guess an archetypical example of model-based reinforcement learning are these agents that learn how to play games. You know, here we've got a game tree for tic-tac-toe, but it could equally be chess, backgammon, Go, any of these games where players take alternate turns. So the game tree represents these alternate turns. So you start with the empty board, you come down, one player places an X, they can choose where to place the X. Depending where they place the X, the next player chooses where to put their O at the next level. So if the agent understands how the game works, then they understand this representation of the game and they can do planning within this representation. And here we can form a plan based just on the estimate of any state value. So for any node in this tree, if we had an estimate of how good it was for our agent, we could easily use one of these well-known algorithms in game playing, Minimax algorithm. I think AlphaGo uses Monte Carlo tree search. There's several ways of solving this problem. But the real difference we want to emphasize today is this is model-based. It requires this knowledge of how the environment works, and it is an easier problem. So in the reinforcement learning research recently, most papers are focusing on model-free. Model-based is not so common. Okay, back to our model-free setting. So here we're going to start describing how tabular Q learning works. So now we've got more numbers. Yeah, it's a slightly more difficult problem. So for every state, we're going to estimate 4 numbers because we've got 4 different actions we can take in any state. So given the start state, we're saying the value of going up is about 0. That's what we're estimating it as. And I should say in this environment, if you go up from the start state, you just come back. So you sort of bounce off any of these walls. So you can see if we had these estimates look pretty reasonable, right? So if we're in the start state, we would choose to go down or across because this 0.1. Now we're here, we see this negative estimate here, so we'd probably go across again. So were we able to estimate these values so well, it would be easy to form a policy that had a good chance of getting to the goal. Okay, so how does it work in practice? So one simple policy is simply to take the best estimated action for the current state. So if we look at any given state, we can find the maximal Q value estimate. So obviously in the start state, there's a tie. You might break these randomly, but if you're in a state like this one, you just take the argmax of these 4 values. So a typical trajectory or rollout would go across, down, and to the goal. Assuming, of course, we did mention at the beginning that the environment is stochastic. So you may take this action to go across, but you may end up in the hole just by chance. But assuming everything works out, we would go across down here, and then straight to the goal. But of course, we need to have these estimates of the values in the first place. So how can we learn them? All right, so we're going to do this using Q learning. This is a value-based algorithm, and we're going to look at how to estimate it. So for Q learning to work, like we said, we're going to estimate this Q value function, and we're going to use a deterministic policy here. So as we showed on the previous slide, we're going to take our policy is just going to be the argmax of Q for the state over all the actions A. For this argmax to work, we need to have a discrete action space. There's no real way of taking this argmax in practice when you have a continuous action space. Okay, so how can we initialize things? Well, we're always going to start with a random estimate of the Q. or maybe a constant estimate. But anyway, it's not going to be a meaningful estimate. We need some way to improve it given our experience of interacting with the environment. And this is where temporal difference learning comes in. So the concept behind temporal difference learning is to unroll for one time step and take the difference. And we can see that in this equation here. So we're going to look at this TD target term first. So we're in state S, and we're taking action A. And we're moving to state ST+1, and we're receiving reward T. So the TD target is the reward we get plus a discounted, plus the value of being in the next state. Yeah, so we can see, so if you look at, if you compare this second term in the TD target and the policy, we can see that the value of being in the next state is just the Q value for the best action we can take in the next state, but we're going to discount it by this gamma. So now what we're going to do, we're going to update our Q value, which is our estimate of how good it is to be in state S and take action A, with our new estimate, our TD target of how good it is to be in state S and take action A. But we're not going to totally overwrite our value. We're going to, this is essentially a learning rate, this lambda. So we're going to take our new estimate, our TD target, how good was it to be in this state, and take this action. Take away our current estimate, so that's a difference. This is a TD residual. We're going to multiply that by a learning rate to control how quickly we learn, and we're going to update our new update our Q value to become a new Q value. I'll just ask if there's any questions here. Okay. And we can see the sort of theoretical motivation for this on the next slide. So let me go there. So this is the Bellman equation. So if in the case, which we often are, where we're using infinite horizon discounted returns, then the Bellman equation gives us this recursive definition of the value function. And it's quite easy to see, right? So the value function is this expectation, as we saw earlier. So it's expectation over all of the episodes that could happen from the given starting state. Now, this reward is this infinite sum. So we can break one term off this sum. Let's take the t equals 0 term off this sum. Yeah, so gamma to 0 is 1. So we're just going to break this R0 off, and that's this R0 here. Then the remainder of the sum is actually gamma times v pi of S1, right? Because what's left is basically the same as r tau, but now starting at time point 1 and with an extra gamma factor. So you can see here we've got a recursive definition of the value function. So we've got the value function defined in terms of itself at the next state. So we see that what's inside the expectation is an unbiased estimator of what we have on the left. And this is really the inspiration for TD learning. So we can go back and we can see this, how this plays into this update equation here for the Q value. So this is the R0 we saw on the next slide. And this is the gamma times the Q value function. Okay, so how does it work in practice? Well, I mean, it's called Tabular Q Learning because it's basically the simplest way to do this Q learning. We store all of these estimates in a table. So for every state, so here's the start state, state 1, we're going to store these 4 numbers. So we just simply need a tabular representation of our Q function. And we're going to have these 4 numbers for every state in every possible state in our environment. Okay, now let's just do a little thought experiment and imagine what's going to happen early in learning. So, so suppose we've got these state action estimates on the slide. Yeah, so we're very early in our learning process. What behavior is going to result? It does depend a little bit on how the policy behaves when there are unexplored state actions. Yeah. So if we start at the start state and we go right, yeah, then we may have already estimated that going down takes us into the hole. So we know we don't want to do that. We've no idea what happens if we go up or across, but we know that going back has got an estimate of 0, right? So if we're just following our argmax policy naively, if we went right from the start state, we'd just come back. And this would definitely be a suboptimal behavior. Okay, we're not falling into a hole, but we're not getting any closer to achieving our goal. So to break out of this local minima, we need to encourage exploitation, right? Sorry, we need to encourage exploration. So there's a couple of ways of doing this. One simple technique is just whenever you see that you could take an action that you've never explored, you choose that. And another method is simply to have some small probability of choosing a totally random action at any point. So essentially you just ignore your policy every so often. And then, in the long run, you're guaranteed to explore all of these actions. But conversely, if we explore too much, we're not taking advantage of any strengths of our current policy for acquiring the rewards, and our return is going to be lower. So in this case, we should explore less and exploit more. So we always have this compromise. How much do we choose to explore or exploit? And in the model-free case, this is particularly bad because we really don't understand what's going on in the environment. In model-based RL, your model of the environment can give you some idea about where actions are going to take you, and you can make much better informed decisions about exploitation versus exploration. So are there any questions? I'm being told there's a question, but I can't see it. Here we go, sorry. So there's some questions about bandits that it looks like Murat is answering. Okay, so the lambda variable in the Q learning slide, yeah, that's quite problem specific. So let's just pop back to that. Yeah, so this lambda is controlling how much you overwrite your current estimate of Q with the new one. So if lambda was 1, you would totally overwrite Q, and if lambda was 0, you would be doing no learning at all. So I'm not sure there's a standard lambda, but yeah, I've seen. Yeah, let me check anyway. Can I come back to you on that one? Okay. Okay, and then just one final point about reward shaping. So this is, well, I mean, Frozen Lake is a well-defined benchmark environment. And in all the previous slides, we showed falling into the hole as a reward signal of -1. But actually, in the real environment, that is the real standard environment that people use, the holes are defined as 0. And this can lead to exploration problems because 0 isn't a strong negative signal for temporal difference learning. So it's hard for the agent to discriminate between bad episodes and just indifferent ones, right? So I mean, falling in the hole is a bad episode, and indifferent one is where you don't really make much progress. So there's this technique called reward shaping, and it's a bit of a heuristic, really. And you know, there's different ways of doing this, but you can choose to give the agent a different reward. For example, for falling in the hole, if you think it will help the agent to learn. So in our case, we find it useful to give the agent the reward of -1 when it falls in the hole. This can really help with Q learning, the convergence rate of Q learning, how quickly it learns. But for any given environment, you know, it's not always obvious what reward shaping is best. So it's kind of an art to choose. It can be something you play with to try and get your agent to learn better. Okay, so those are the slides. I'll ask for any questions again. But now we'll be moving on to the exercise. So I hope you've all got access to this, to first of all, this website. And second of all, if you go to the website and you go to the quick links section, it's going to take you to our GitHub repo where you'll find a notebook to do the first exercise. And in that notebook on GitHub, you can click on the Open in Colab button, and you should be taken directly to Colab where you can start running the exercise. And it should be self-contained, but obviously we're here to answer any questions as you go, and we would encourage that. So yeah, please let us know how you go.
So it's now 9:10. I hope most of you got a chance to go through at least most of the exercise. Obviously, the exercises will be available to you later on, so no worries if you didn't manage to go through all of it. But yeah, to stick with the timetable, we should continue now. As John had just mentioned, for the next exercise parts, it would be good if we can use the Q&A functionality for the questions so that we are not in the main chat. This is all a bit unorganized, but if you click on the bottom of the Zoom application, there's a Q&A button, and there you can ask questions and we can answer specifically to your question. So it doesn't get all lost in a messy chat. Other than that, let's continue with the slides and come to Q learning, deep Q learning. So let me just start them. And I hope you can see the slides now.
Yes, we can, Alex.
Yeah, good. All right, so we'll continue with deep Q learning now. So tabular Q learning really is has already been around for a long while, since around the 90s. So this is really an established technique, but it has a lot of limitations. So it's useful in some applications, but then there are limitations. And deep Q learning was one of the early breakthroughs in the deep learning era in reinforcement learning, in particular coming from DeepMind. And I'll come to that in a bit. But first, what is the problem with tabular Q learning? Now, as John has said, what we're doing in tabular Q learning is really the simplest way of storing our Q values. We're just storing them in a table. And if we imagine that we have a scenario where our application is non-trivial, it's not a frozen lake, but it's something more complex, then we have, let's say, 10,000 states and 10,000 actions. So we would need to maintain a table with 100 million entries, and clearly that's not really feasible, and that doesn't scale very well. So the motivation here is, can we learn a function that does the mapping for you? So instead of storing things in the table, can we learn a function that maps state action pairs to their corresponding value? And deep Q learning networks, which is DQN and abbreviated, is using deep neural networks for this mapping. Now to make it a bit clearer, what is the problem? So this is one of the Atari games, which was part of the early breakthrough of DeepMind. They use DQN to solve a lot of these Atari games. And as you can see, Atari games, you have an image input, and images are very high dimensional. So storing images in a table is really very quickly gets unfeasible. And so also there are lots of minor variations between images. So we could, for example, imagine that during inference, we just see a slightly different constellation of the screen, but we haven't seen that before. So we don't have any information about that screen. So we basically don't know what to do. And this can happen very frequently. And so by leveraging a neural network, we can solve a lot of these things. First, we can handle more complex states like images, which, as I said already, are not easily represented as table entries, because deep learning is very good at extracting features from high dimensional inputs. So it's a way of compressing the input into a more meaningful, smaller, lower dimensional representation. It's moreover able to learn similarities between states. Because we are compressing, we can basically learn that some screens should really be treated as the same. And we're not considering each screen where just one little element is different as a completely different state. And that helps because we are then, with each observation, we're not just learning for that very specific screen, but we're learning for like a range of screens that look similar to the one that we observe. And that's also the reason why we are able to react to previously unseen states, because as long as we've, during training, observed states that look similar, we can most likely generalize to this unseen state later on. Now, there are, of course, limitations to all of this. For example, I need to have seen similar states during training. Otherwise, I still don't really know what to do. But as long as these restrictions are satisfied, deep Q learning would hopefully work very well. Now, for the ones who have not much experience with neural networks, here's a very quick recap of what neural networks are doing and how do they manage to learn to handle high dimensional inputs. So basically, a neural network consists of nodes, which are the neurons of the neural network, and connections between these nodes, which are the synapses. Now, this comparison is not far from perfect and shouldn't really be used, but that's why the things are called neural network. And the neurons, they are structured in, and they are aligned in layers. So you have an input layer, then you have a hidden layer or multiple hidden layers, and at some point you have an output layer. And so the input to a layer are the outputs of the previous layer. And each layer, each neuron in a layer takes the outputs of the previous layer, all of them, and combines them in a weighted sum, and then applies an activation function, a nonlinear activation function. And the learning happens in the weights. So the weighted sum, these weights that we're using to weight the inputs, are the weights that are learned in a neural network. And they are usually learned via a gradient descent based on a loss function. So we define a loss function on the output, and we are then using gradient descent to minimize this loss. And we need a training data set for that, where we have the input output. So we given an input, we know what we expect as an output. So we can then compute a loss between what we expect and what a neural network gave us. And if we have enough data, neural networks are very expressive. They can learn to represent a wide variety of functions. In fact, there are theoretical proofs that they can approximate any functions given a big enough network and enough data. Now, in DQN, we now change the setup slightly. I so far said that what we want to learn is a mapping from a state action pair to a value. We are not gonna, DQN is not doing it quite in that way. What it does is it maps a state to the value of all the actions in that state. So the reason really is that we only need to evaluate our network once per state. So that's more efficient. Remember that we need to compute the maximum or argmax of the Q values for one state. So we need all the Q values for that state. So by formulating it this way, we only need to compute the output ones. Also remember that computing neural networks is expensive, potentially, computationally. Now, yeah, during inference, we do the same as before. We take the maximum of all the action corresponding to the maximum Q value in that state. And if there are multiple maxima, we randomly break ties. And during training, we again also use an epsilon greedy algorithm to balance exploration and exploitation. Same as before. That means we, with probability epsilon, some small value, we select an action at random. And with probability 1 minus epsilon, we choose the optimal action based on our policy. And DQN is also trained in the same way as Tabular Q Learning. So we have the temporal difference learning, where we're computing a temporal difference target and then the temporal difference residual. And then we're updating our Q values like that. Now, DQN, I mentioned neural networks are always trained with a loss function. So what we're doing here is we are using a loss, which is just the difference between the TD target and our Q value estimate. And if we would compute a gradient of this loss function, we would basically, and we would put the gradient in an update step, like gradient descent does, we would basically end up with exactly the same expression as above. So that's in short how DQN works. Now to summarize, what are the advantages of DQN? First, we compress the Q table so that we can handle high-dimensional state spaces. We can now handle states that have not been seen during training, thanks to the ability to learn similarities between states. We are using the Q network, which acts as the feature extractor, so that we can generalize to states that we haven't seen and just get more signal during training for each observation that we observe. And also a benefit, which is in contrast to an algorithm that we come to later, is that we can use both on and off policy updates. Now, what does that mean? On policy is the data that we collect from our current policy, whereas off policy is data that has not been collected by our policy, but that we just get from somewhere. And that could in particular be experiences that we had earlier on in training. So these experiences, they are not collected by the current policy. They are collected by an earlier version of the policy. But DQN is able to use both of these for learning. And that means that it's very sample efficient because we can basically reuse earlier observations later on in training. Remaining disadvantage of DQN is that it cannot handle continuous action spaces. Why? So it can handle continuous state spaces, but not action spaces, because we need to compute the maximum or argmax over all the actions. So we need a discrete set of actions in each state, which we can compute the argmax over. A practical approach to address this would be to discretize the actions, but that would, of course, introduce a simplification of the environment that might not be good. Another disadvantage is that it is deterministic. Well, this is not necessarily a disadvantage, but it can be, in particular, in the context of the next point, which is that we have this separate epsilon greedy algorithm to balance exploration and exploitation. Because our policy is deterministic, there's no exploration would happen unless we introduce this epsilon randomness to sometimes just take a random action. However, this random action is not very informed. They're just doing it at random moments during training, and that there are better ways to do that, but not within a deterministic policy framework. Okay, now to also cover a few popular extensions to this main idea behind DQN. The next two, they are part of the original when DQN by DeepMind was introduced in 2013, I think. These extensions were necessary for them to train DQN successfully. The first one is experience replay, which basically refers to each observation that we collect. We're going to store it in a memory and a replay memory, and then for updates we randomly sample from this. We randomly sample observations from this replay memory. The effect is that the experiences that we use for updating are not correlated in between them, which can be a problem for learning if the experiences that you use to update are highly correlated because they're all collected from the same episode, let's say. This can lead to overfitting in the neural network in unintended ways. So by having this randomly sampled observations, we are preventing the learning to overfit. And this is also inspired by how the brain might learn by randomly sampling experiences during dreaming also. And the second one is a target network, where this is really a technical detail. So on the bottom you have the TD learning expression. And so now instead of using our Q function as when we compute a temporal difference target, we're using a separate network, the target network, to compute this Q value. And this target network it's like an older version of our main network. So it's synced infrequently with the main network. It's like a lagging behind version of the main network. And the reason is, again, related to correlations. We want to reduce the correlation between the target that we compute here and the Q function that we're currently training, because otherwise there's a very recursive feedback loop, and this might affect learning in unintended ways. So by having a more stable target, we we get a more useful learning signal. And so these two modifications were part of the original DQN implementation, and both of them were necessary for DeepMind to apply it successfully to the Atari domain. Then in the years since then, there were lots of additional extensions. One, for example, double DQN, which again changes the expression of the TD update slightly. Now, the modification here is that instead of, let me go back. So what we did here, we choose, when we compute a temporal difference target, we choose our action based on the target network. And then we take the value corresponding to that action according to the target network. Now in double DQN, the difference is that we're still using a target network, a Q target, to compute the TD target, but we're choosing the action not based on our target network, but based on our current network. That means that we're using as the value of the next state, we're using the action that our network right now would take, but we're using the value according to the target network, which is an earlier version of our main network. And this was again found to improve the learning signal slightly by using more accurate estimates of the next state value. And there were many more. One, for example, prioritized replay memory. So instead of using a random replay memory where we randomly sample experiences, some experiences are more useful than others for learning. So prioritized replay memory introduces a sort of ranking of experiences and favors, when randomly sampling experiences, favors experiences that are probably more useful based on the loss. So that the higher the loss was for that experience, the more there was to learn. So the more often this experience is sampled. And another one is dual DQN, which is changing the setup slightly, the way how to represent the Q values. So Q values are state action values, and they can be split into a state value, which is like the base value of being in that state, and then an advantage value, which gives like the relative advantage of taking a specific action in that state. And by splitting it up that way, you're splitting learning to learning the value of a state, which is a more general task, and then learning the relative benefit of an action within a state. And that, again, is a slight change to the formulation of the optimization that seems to help learning based on gradient descent and neural networks. So most of these tricks are really related to also just the way optimization with gradient descent for neural networks works, and empirically what works better, what allows us to train networks better versus what doesn't work so well. And yeah, that's in short an introduction to DQN and some of the extensions. We now also have exercises for DQN where you can experiment with some of the things mentioned on your own. But I think first of all, we'll have a break now for half an hour. So it's up to you. We'll continue after the break at 10 for half an hour with exercises. You can take a break whenever you want. You can do the exercises whenever you want. We will still be around answering your questions even during the break.
Hi, everyone. I hope that you have had some fun playing on the slippery frozen lake. Can you see my screen? I'm Dell Zhang. I would like to talk about the applications of dequeuing in information retrieval. So we think that dequeuing and the other algorithm reinforce are the most used reinforcement learning techniques in recent IR applications. And more importantly, dequeuing and reinforce represent two different approaches. And once you have known these two techniques, it will be easy for you to understand and utilize the other reinforcement learning algorithms in their corresponding families. So in the afternoon, my colleague Murat and I will continue the discussion of IR applications using the other algorithm reinforce. So to use reinforcement learning for information retrieval or any other real-world application is kind of similar to the solution for how to put an elephant into a fridge. You only need 3 steps. Open the fridge, put the elephant in, and close the door. So similarly, to solve a real-world problem like information retrieval using reinforcement learning, you only need 3 steps. First, you would like to formulate the problem as a Markov decision process. Second, choose a reinforcement learning algorithm for the Markov decision process. Here we are using dequeuing as the typical reinforcement learning algorithm. And in the end, run the reinforcement learning algorithm to get the results. So before we go further, I would like to mention that in information retrieval, you probably have seen many applications of the so-called bandits, particularly the multi-armed bandits, where you can consider these bandits as a row of slot machines. People could choose different arms and get the rewards. In search and advertising and recommendation, so more people are using the extension of the multi-armed bandits, where you have access to the contextual information. So roughly speaking, contextual bandit is a simplified version of reinforcement learning, where you only have to consider just one step. Whereas in reinforcement learning, you need to consider the sequence of actions, and the reward often would only be received at the end of the sequence. And it is because of this sparse reward problem that there's the difficulty of assigning credits to the individual actions that you have chosen in the past. So here in this tutorial, we're going to focus on the full reinforcement learning problem. And the first applications in the IR field using reinforcement learning come from the recommender systems. So we have all been familiar with the recommender systems, which are widely used nowadays by different internet companies. These systems are very helpful to mitigate the information overload problem by making personalized suggestions to the users. This could be formulated as a sequential decision problem particularly when the recommended system is going to have a multi-step interaction with the user. So quite often the user is having an account on the website, and the recommended system would make recommendations. The user may like the recommendation or not. So this feedback could be used to refine the recommendations in the future. But there are many effective techniques that have been developed in the past for recommended systems, such as the nearest neighborhood methods or the more effective factorization machines. And in these traditional techniques for recommended systems, the recommendation procedures would be considered as static processes. And they follow a fixed strategy in the sense that these strategies are not changing according to the responses from the users in real time. And the objective was often to maximize the immediate or short-term reward from the users rather than their long-term interest or the long-term engagement. So using the reinforcement learning technique, it is possible for us to continuously update the recommendation strategies so as to optimize the long-term reward from users. So roughly speaking, the recommended agent would make the recommendations based on the browsing history of the user, and the recommendations would be the actions taken by the recommender agent. The user would indicate whether they like the recommendation or not by whether by choosing to purchase the recommended item or just ignore them. So these rewards would be used to help the recommender agent to make a better recommendation in the future. So the recommender system would benefit from this kind of sequential decision making because, for example, if the user has accepted the recommendation of buying a new bed, then it is likely that the user may want to buy the mattress or the duvet or the pillow. So if you make a series of recommendations, then there's more space for you to optimize and hopefully get make more profits from these recommendations. So the there are many papers talking about the usage of reinforcement learning in recommended systems. So I have chosen some which contain some useful tips and tricks when we apply deep learning to recommended systems. So the first paper comes from the Pennsylvania State University and Microsoft Research Asia. So it is about the specific problem of news recommendation, but many of these techniques could be generalized to other recommended systems. And here, the motivation is to model the long-term effect in recommendation. For example, this figure, we see that a user is requesting for news items, and the recommender agent has two options, or two possible items to recommend. One is a news item about the basketball player Kobe Bryant, and the other is about a thunderstorm alert. So at the current step, the recommender system may consider that these two options have equal probabilities to be liked by the user. Right? So, however, if you look further ahead, then there could be different amounts of rewards. If the user has read the recommended news item about the thunderstorm alert, maybe he is not needing to read any more news items about that. But after the reading the news article about Kobe Bryant, he or she may like to read more news items, news articles about basketball or NBA. So this seems to suggest that recommending the piece of news about Kobe Bryant will introduce much larger future reward because it would be able to engage the user later. So this is the example. Of course, it's not necessarily true that every user is going to like reading NBA news, but at least this seems to suggest that there's more space for us to optimize through the usage of the reinforcement learning algorithms. And the recommendation of news is a dynamic problem because according to the statistics, the life period for news is usually very short. In average, the life period measured by the difference between the last click time and the publishing time of the news item is roughly 4 hours. So moreover, the user's interest may change along with time. So this graph shows the category of news that one user has read in 10 weeks time. So during the first few weeks, we see that there's a long bar in green that indicates the consumption of political news. But gradually, the user's interest moves to the purple and the gray bar, which correspond to entertainment and technology. And so the user's interest has gradually changed over time in these 10 weeks, which is a common phenomenon in news recommender systems. Furthermore, sometimes we may want to use the user's feedback other than just the clicks or the skips. For example, a useful signal would be the frequency of the user returning back to the website. How soon a user will return to to our service will tell us how satisfied this user is with our recommendations. And we would benefit from a framework which can incorporate such signals as the feedback. So there are a number of challenges in news recommendation. One problem is whether we want to increase the diversity of the recommendation. For example, if we keep recommending news from NBA when the user is browsing the sports news, the user may get bored. It might be better to adjust the level of diversity according to the user's interest. So the research on the reinforcement learning for news recommendation is motivated by the optimization of long-term effects in recommendation. So to deal with the challenge from the dynamic nature of news recommendation, we could make use of the online learning feature of reinforcement learning, where the agent is continuously updating its policy. And to incorporate more measures for the long-term effect rather than the immediate reward, we could design different reward functions for reinforcement learning. And this gives us a lot of the flexibility. To increase the diversity of recommendation, we could benefit from the exploration built in reinforcement learning algorithms. So first, let's see how we can formulate the problem of recommendation in general as a Markov decision process. So the environment would include both the pool of users and the pool of news items. The agent is the recommender system or the recommendation algorithm, which makes use of the reinforcement learning algorithm as the basis. So here the users would be considered as the states. So the user would have a number of different features which would tell us the recommender system about the user's potential interest. So the action that needs to be taken by the recommender system or the reinforcement learning algorithm for recommendation is the set of the news items. So at each time step, the reinforcement learning algorithm needs to choose a suitable news item that can be pushed to the user. And hopefully the user would be able to click on the recommended news item. So the reward would be the function designed to capture the user's feedback, either positive or negative. So if the user has clicked on the recommended news article, then the agent would receive a positive reward. Moreover, you could incorporate other useful signals, such as the user activeness. So the entire model would consist of both the offline stage and the online stage. So it has the reinforcement learning agent would need to be trained on the offline data that consists of the interaction logs for all the users in the past. So this is to give the recommender system a good start. But more importantly, the benefits of the reinforcement learning algorithm would be shown when it goes into the online stage, when the reinforcement learning agent is going to continuously interact with the users, receiving the feedback and refining its policy. So in the offline stage, there could be multiple types of features that can be extracted from the news items and the users. Then we could train a DQA to predict the reward for this, based on these features for the candidate news items. So these offline training could be carried out from the offline past user click-through logs on the news items. Then in the online stage, the reinforcement learning agent will interact with users. So the network will be updated for the DQA in real time. But the training or the adjustment of the neural network in DQA would take time. So in practice, it would be a good idea to include, to sort of have the quick minor updates after each time step. So you just train the using the training algorithm of DQA to improve the network but within a short time period, rather than sort of having the full training, training until you got the convergence. And so this is to ensure that the recommender system is going to be responsive and working real time. So after each time step, you do these minor updates within a fixed short time period, and then after a while, there may be the network would need to be updated based on all the data. For example, let's say after 1 hour, the network in DQA could be updated. So this combination of the minor updates and the major updates are common practices for real-world recommender systems when they are applying DQA. So the next trick is to divide the Q value to be estimated using the DQA into two parts, the value and the other, which is called the advantage. So here the advantage simply means the difference between the value, which depends on the state only, and the Q value, which depends on both the state and the action. So here advantage measures how good the specific action A is on the state S. So compared to the kind of value function for the for S. So this architecture is called the dueling network. Intuitively, the benefit is that you could have a simpler network architecture, which would be easier to train and more likely to achieve better performances, because the value function which is measures how good the state is. It depends only on the state. So here it's the state is about the user. So this part, the value function, could be calculated by using only the features about the users themselves, and also the features about the context. But in addition, if you want to calculate the full Q value about the choice of an action A in state S, we would also need to incorporate other features, such as the features about the news item, and also the interaction between the user and the news item. So in other words, the calculation of the Q function would need 4 types of features, but the calculation of the value function would only need 2 types of features. Therefore, if we split the have a subnetwork to estimate the value of for each state, then it would be easier to be trained and easier to learn from these features. So the specific goodness of the action A would be estimated by using all the other, by including all the other features together. So this is the so-called dueling architecture, which has been found to improve the training effectiveness of deep learning. Right, so the reward function, as we have mentioned, include not just the simple click or skip activities carried out by the user, but also you could add some other information. So in the end, it's just a function that you could optimize. So in this case, they have tried to use the frequency of the user returning back to the recommended system. So they call it the user activeness, which is measured by the so-called hazard function, which is a technique from survival analysis. So this is beyond the scope of this tutorial, but the bottom line is that in the design of the reward function, you could incorporate many different types of these useful signals. Right. So another problem in the usage of decoupling for recommended system is that the exploration policy commonly used in decoupling would be problematic, because quite often you see that in decoupling papers they talk about the usage of the so-called epsilon greedy strategy for exploration, which basically means that with a small probability at each time step, the agent would choose the action randomly, and that would be detrimental to the user experience of the recommended system, because if they see some totally irrelevant recommendations, but the users would not be happy with that. So the a better way to perform the exploration, which is necessary to have the best performance for reinforcement learning algorithms like decoupling. So they developed this technique called dueling Bennett gradient descent. And here the idea is that we just want to use the item not completely random, but a random, a sampled item from the small neighborhood of the current recommendation. So in addition to the current network, one could construct the so-called Explore network. The Explore network is a slight modification, right? A slight change of the current network. So, for example, the model parameters or model weights would be in this DQA, and would be some small perturbation of the current weight, and then in this way you have a decoing network which is similar but not identical to the current network. Right. So we could generate the list of recommended items using the current network Q, and also we generate another list of the recommended items from the Explore network. So these two lists could be interleaved together. For example, we choose AB from the first list, AC from the first list, and CD from the second list. So in the end, we have a combined list ACD, and then we could get the feedback from the user about these, whether these recommendations are accurate or not. So if it turns out that the recommended item D is the best recommendation for the user, then we know that the Explore network is on the right direction. So we would update the current network towards that. So if it turns out that the recommendations from the Explore network is better, then we would update the current QNet degrade by slightly changing the current model parameters towards the direction of the exploration. So here, this is the learning rate. Right, so next, let's have a look at the another paper on the usage of decoding for recommended systems. And this work comes from the Michigan State University and also the researchers in JD.com. So JD is a counterpart of Amazon in China, which is a large online shopping website. So the in this work, the authors have argued that it would be beneficial to use both the positive and negative feedback. But most of the recommended systems would use the positive feedback only, such as whether the user has clicked the news item or purchased the recommended item. But sometimes the negative feedback, when the user has skipped the recommended items, could also be helpful. And this could be incorporated into the reward function. So if we want to achieve that, then it would be better to use a different network architecture So here, the point is that we may want to have two separate networks, one for the positive feedback and the other for the negative feedback. So here the state would incorporate the information from the recommendation session. So each time when we have a session of interaction with the user, this could be put through a recurrent neural network called, for example, using the gated recurrent unit, the GRU. And then this sequence of interactions in a session would be incorporated, would be encoded as a state vector. So here you could use all the items that have been clicked or purchased. So in other words, the positive feedback. And in the same way, we could encode the negative feedback in the user session into negative state vector. So the here the idea is that we would like to recommend an item that is as similar as possible to the clicked or purchased items, but while as dissimilar or as far further away from the skipped items as possible. Therefore, if we split this decoying network into two separate parts, then the architecture can help the decoying to capture the different characteristics of the positive items and the negative items separately. So this again, would help the system to help the decoying to learn more efficiently. So we have also considered the trick of modifying the reward function. So they call it the pairwise regularization. So here, one example is given in this graph. It shows that in one recommendation session, we have three categories of items, A, B, and C. So the users had the interaction with the system in this sequence of steps. So the for example, for category B, let's say it's about mobile phones, then the user has clicked on the item A2, but skipped the item A5. So A2 and A5 are both mobile phones. So when training the decoying, we would like to make use of these prior knowledge that users are very likely to buy just one item from the same category. It would be very rare for a user to buy two different phones in one go in the same session. So this is the kind of the prior knowledge of the mutual exclusiveness between the items in the same category, which makes sense. So this heuristic of mutual exclusivity has been utilized in some other work for self-supervised learning. So this is a useful signal which could be used to regularize the Q function. So here, because we think that there's at the most one item that could be accepted by the user as the useful recommendation, if they are coming from the same category, then in the training of the in the reward function, we would want to maximize the difference between the two Q values. So the here in the loss function, the first term is the difference between the ground truth and the estimated Q value. So this is the empirical loss, and the term here is the difference between the selected item, the action A, and the another competitor item in the same category C, which has not been accepted by the user. So here, for example, this is A2, but this is A5. Okay, for category B. Now, yeah, so in one category, there could be multiple competitors for the selected item. For example, in let's say at the time step 3, in category A, the user have chosen the item A3. So in the same category A, there are two other items, A1 and A6. So in this case, to formulate this pairwise regularization term, we just choose the competitor with the closest time difference between from the selected item. So in this case, we would have constructed the regularization term using the clicked item A3 and the closest skipped item A1 for category A. Now let's look further at the work that has been done by the same group of users, the authors from the Michigan State University, and some other researchers from ByteDance. The ByteDance is a big internet company in China, which has developed the well-known TikTok platform. So they have tried to use the TQA for both recommendation and advertising at the same time. Traditionally, recommender systems and advertising systems are developed separately. And for the recommender systems, the goal is to maximize the long-term user experience or engagement. The challenge here is the huge action space due to the combination of actions. If we want to recommend a list of items, so this combinatorial action space grows up very quickly. when we want to recommend more items to the user. So for the advertising systems, the objective is to maximize the advertising revenue, but at the same time, you would also want to minimize the negative influences of the ads for the user's experience. So here, the way to add the adverts to recommended systems is simply to insert a chosen advert to a particular position in the list of the recommendations. So here we need to make several decisions. Should we interpret the recommended list with an advert or not? Considering the possibility of getting more revenue, and also the possibility that it would decrease or hurt the user experience. And if we do want to add the advert so that it, to interpret the advert with the list of recommendations, then we need to find the best location for this advert, and also to find the optimal advert. So these are the challenges for us to consider when we want to combine the advertising with the recommended system. So the process is like this. The typically user would browse the mixed recommendation and advert list, right? And then the user would provide the feedback. So for example, the user could have chosen a recommended item, or the user could have clicked on the advert. So this kind of feedback would be supplied to both the recommended system and the advertising system. So we could consider these two systems, one by one. So let's say to reduce the complexity of the entire system for both recommendation and advertising, we try to construct the list of recommendations first using the recommended system, and then in a later step, we make use of the advertising system to decide whether to add an advert to which position, and to construct the final list of items. So eventually, this could be done using two deep learnings. So the first level is to is the deep learning for the recommended system. And the second level is the deep learning for the advertising system. Now, when the user has seen the mixed list, the user would provide the feedback. So this the reward could consist of both the reward for the recommended system and the reward for the advertising system. So this reward would be split into two separate parts. The reward for the recommended system, together with the state, would be provided to the recommended system DQA. And then after the recommended system using the DQA has decided the list of recommendations, this would be added to the user state. So the actions from the recommending DQA would be supplied in addition to the state describing the user as the input to the advertising system DQA. So the second level DQA is responsible to construct the final mixed list, including the recommended items from the first level DQA and the items that the second level DQA itself is recommending to add as the editors. So the architecture is shown in this figure. So the first for the recommendation system, there's the challenge of the combinatorial action space when we need to recommend a list of the items. So one commonly used trick here is to use sequential approximation. So rather than generating a list of the items directly, the DQA could consider it as a sequence of selections. So the if we would like to recommend a number of items, then we could use the DQA algorithm to choose k items from the large item space one by one. Right. So this is because the combinatorial action space that includes all the possible combinations of k items would be too big, and it would generate very high computational complexity. Whereas the and also the order of the items in the list also matters. And so the idea of the cascading DQA is that you generate the list by selecting these k items one by one in a sequence. So each time you just choose the item for the current position in the recommendation list until you have chosen k items. So here it's mainly the point is that the action space could be reduced greatly by sequentially choosing items. And similarly, as the previous work, we see that the sequence of recommendations in the past, the historical recommendations, and the adverse, that the user had collected in the past, these would have been encoded using recurrent neural networks, such as ASTMs or GC. These encoded vectors capturing the historic recommendations and adverse would be combined together with the counter context to form the state vector. But the advertising system could be done in a similar way, but there are some additional challenges. Right? So the problem is that we would need to decide at the same time the answers to these three questions, whether to insert an ad to the currently recommended items list, and where to insert the ad, and also which ad to insert. So the also solution is to propose a decoupling architecture that can address these three decisions at the same time, which is so this architecture is kind of different from the standard ones. In traditional decoupling, either the network is receiving the state and output the a number of Q values that corresponding to different actions. So in the end, you choose the Q, the action corresponding to the highest Q value. Or in some other decoupling implementations, both the state and the action would be supplied as the input to the neural network, and the Q value for the given state ST and the particular action AT would be estimated using the network. So here, what they have done is to extend the this decoupling architecture to include not just one, but k plus one outputs. Right. So we have the Q values corresponding to the state ST, and the action for the particular ad at AT. So these combined together would be used as the input, but for the output we would have k positions, each corresponding to a different Q value. So we have the k plus one positions. If we are given a list of k items, so there are k plus one different positions to insert. Right. So, for example, if we will have 3 items that have been recommended, then the advert could be inserted to the at the beginning, right here, yeah, and at the end. So for k recommended items, we have k plus one possible positions to insert one advert. And there's, in addition, there's also a special output, which is for the at the beginning, shown in this list of outputs. So this particular one actually corresponds to the action when the system decides not to insert any ad. So this one is means no ad. So when the decoupling has calculated the Q values of this k plus 2 output neurons, then if in the case that the first neuron, the Q value is the highest, the system would decide not to add any advert to the list of recommendations. And then if one of the other outputs has the highest value, you would choose to add this particular ad into the corresponding position in the recommended list. So furthermore, we want to stress that, because the task of the second level decoupling is to just insert the add into the given recommendation list. So the output from the first decoupling would be added at, so this is the decoupling for the advertising system, the second level decoupling. So here, in addition to the previous state vectors capturing the historical recommendation, the historical adverts and the context, we would also want to make use of the list of recommendations generated by the first level decoupling. So as the input to the advertising decoupling. So this shows the network architecture, and similarly, you could make use of the dueling network architecture that separates the value and the advantage. So this is the overall architecture for the advertising decoupling, which is built as the on top of the previous decoupling for recommendations. So in summary, so we have discussed how recommendation or advertising could be formulated as a Markov decision process. So the users would be considered as states, and the items to be recommended would be considered as the actions. So the tricks that have been used by the researchers and practitioners in this area include the offline training in advance, and the combining of minor updates and major updates in the online stage. So it has been found to be useful to use the dueling network architecture, which estimates the value and the advantage separately to compute the Q value. And then the idea of using an explore network in addition to the current Q network for beta exploration without hurting the user experience too much. And then it would also be a good idea to separate the decoupling network for positive and negative inputs. And then you could add this pairwise regularization that enforces the mutual exclusiveness of items in the same category. So to address the combinatorial action space size, one could use the generation of actions as a sequence in the cascading way. And these decouplings could be stacked one above the other if you would like to perform both recommendation and advertising simultaneously. So that's all that I've wanted to present about the usage of decouplings in recommended systems and advertising systems. Okay, so I will stop the presentation here, and let's take a lunch break. So if you have questions, you're welcome to ask using the Q&A channel. So I will be here and try to give you my answers for your questions. But if you'd like to have your lunch early, then that will be totally fine. So I'm going to stop the sharing of my screen.
All right, let's slowly get started. I hope everyone made it back. So now the second half of the tutorial will be focused on policy gradient methods. So far, we've looked at Q learning. We've seen tabular Q learning. It's like the approach that has been around for very long. And then deep Q networks, which are the modern variant of Q learning using deep learning to use neural networks as function approximators. And now in the second half, as I said, we look at policy gradient methods, which are an alternative class of algorithms for reinforcement learning. Q learning were value-based methods. So central to their algorithm was the fact that you learn a value function. In the case of Q learning, it was the Q value function. And then you derive a policy from this value function. In policy gradient methods, we don't learn a value function, or at least it's not central to the algorithm, but we instead directly learn a policy. But let's first start with a few motivational points. One of the shortcomings that we've seen is that Q learning cannot handle continuous action spaces. The main reason for that is that computing the argmax over a function, over a continuous function, is in general pretty difficult. So this is a fundamental limitation. Second point, Q learning is not compatible with a stochastic policy model. So we've seen that we learn a value function and then we have a deterministic way of inferring what action to take from that value function, which is the argmax. And then we also sometimes sample our action, but that's really a hack to introduce some exploration into the method. The method itself is deterministic. And sometimes in general, stochastic models are potentially preferable because of, for example, the ability to naturally balance exploration and exploitation. If you have a stochastic model, you can incorporate exploration versus exploitation in your model model framework. And finally, and most importantly, Q learning is not directly optimizing the policy. That's really a core difference. What we do in Q learning is we're learning a value function and then we derive the policy from it. And this is the way we do it. It's a greedy approach. So at each time step, we look at our values and we take the maximum. And that might not be the most optimal way. Certainly, we're not directly optimizing our behavior. We are indirectly doing it via learning a value function. And that's the main point of the policy gradient methods. Let's try to optimize the policy directly. So in policy gradient methods, hence, instead of using a value function, we directly look at a parameterized distribution as the policy, and we are trying to optimize these parameters. This is now generally framed as a maximization problem. So instead of minimizing loss as before, here we are maximizing performance. And we are maximizing performance based on a measure of performance, which is here noted by J. And so we are kind of taking steps in the direction to optimize our parameters to maximize this performance measure. And usually the performance measure is the expected discounted return. So we've seen that before. Now, maybe important to note that we are not optimizing the reward at each time step, but we're optimizing the episode return, because we want to look at the entire episode and get the best possible result for the policy for an episode. And we don't just want to greedily optimize the policy to do the best possible in each time step, which might be not the best thing to do. Maybe sometimes you need to do a suboptimal action to later on maximize your overall reward. And so we want to take that into account in our formulation. And so when we look at this and we want to use, like we're in deep learning, so we want to do it via gradient descent, or here gradient ascent, we see that we have a problem because our policy is stochastic. We are trying to maximize the expected return, and so we have a gradient over an integral which is dependent on the probability of trajectories. And so this is all not as straightforward to compute. First, because the action selection within a trajectory depends on the policy. And second, then the trajectory reward indirectly also depends on the policy, but also on the environment. But fortunately, with some math reformulations, we get the policy gradient theorem, which tells us that basically the expectation and the gradient can be swapped. So instead of having the gradient of an expectation, which is hard to compute, we're getting the expectations of an expression that involves the gradient. More precisely, we're getting this expression at the bottom, the return of a trajectory multiplied by the gradient of the log probability. And yeah, if you're interested in how to derive this, it's not that difficult. You can, I think, find it in most papers or introductions. But it's not important. That the fact is that is important is that we can do that. And so now the question is, how do we estimate this expectation? And usually in the simplest variant of policy gradient methods, also called the reinforce algorithm, you just use a Monte Carlo estimate. So how does that method then work? We're starting off with random parameters for our policy distribution. Then we are generating episode trajectories. So we're just running a few episodes on our given problem environment. So we're collecting experience, and this is on policy experience. Then we are computing the discounted episode return for each of these trajectories. And then for each time step, we are performing this update gradient ascent step, where we are shifting our gradients slightly towards more optimal performance based on the observation. And then we'll continue with 2. So we generate new episode trajectories so that they're again on policy observations, and we're doing the same process again. It's important here that all of this only works, at least based on the mathematical derivation, if the trajectories are collected on policy. So different from Q learning, where we were able with like the replay memory to, for example, also reuse older observations. Here we can't reuse older observations. We have to collect new on policy observations, which we then base our update on. Okay, now what does this look like in practice? First, of course, we use a neural network to parameterize the policy distribution. And this neural network, similar to before, really takes in the state, the current state observation as input, and outputs a distribution over actions. So like previously, we had the Q values for each action. Now we output the probability for each action, at least in the discrete case. If we have a continuous action space, we, again, what we are in general doing is we are parameterizing a distribution. Now in the continuous case, we have to decide what action distribution do we want to use. Generally, people use like Gaussian normal distribution. And so what the network in that case would output is the mean and the variance for each input, for each state. And that then parameterizes the normal distribution, which gives us the action. There are some variations sometimes. Some people only parameterize the mean and use a standard variance. But yeah, this is maybe one general formulation of how to do it. And another little detail, I've initially said that we are now doing gradient ascent. In deep learning, most frameworks, however, are fundamentally based on doing gradient descent. And so if you want to turn gradient ascent into gradient descent, you just put a minus and then you're minimizing the expression. So instead of maximizing based on the return times log probability, we are now introducing a surrogate loss, which is minus return times the log probability. And then we can use deep learning frameworks as we're used to with a loss that we have to minimize. Now, note that this loss is a surrogate loss because we're not really minimizing a loss, but this loss, when we compute a gradient, will yield us exactly the expression that we want. So it's, so to speak, it's the loss that we are implicitly minimizing, even though it's not a proper loss. Not proper loss in the sense that this is not a loss that you can minimize to zero also. This loss can be positive, it can be negative, but what you want to do is you want to minimize that expression. All right, few more points. First, but given the fact that we sample from the policy during training, so we're not deterministically choosing the maximum action, we're sampling from the distribution. I've said before that this naturally balances exploration and exploitation. Why is that? Essentially, as training progresses, the probabilities shift towards the actions that led to high return episodes. And so at the beginning, we start at a random distribution. And then over time, the probabilities of the actions that were more beneficial get higher probabilities assigned. However, this happens to the degree that these actions were useful. So there might well be actions and states where even after a long training process, it's still relatively uniform distribution because in that state, it just doesn't matter which action you take. Both lead to good or bad outcomes. And so in that sense, it naturally introduces this exploration-exploitation trade-off. Whenever an action is very important or whenever one action decision is much preferable over the others during training, it will learn to exploit that very much. And whenever there's little difference between the different actions in a state, training will not really shift the distribution very much and it will remain uniform. And this is quite important in comparison to Q learning, because Q learning infuses exploration completely randomly, at least if you use simple approaches like an exploration rate, like we did. And this purely random exploration is not as good as exploring where it makes sense and not exploring where you're very sure that you don't want to explore, which is what happens here. The second point is each training update impacts all actions for a given state. Unlike Q Learning, where what we updated is we updated one specific Q value, so one specific state action value. Here, we are also only shifting the probability mass for one action, for the action that we took as part of this episode. However, by shifting the probability mask in favor or not in favor of this one action, we are implicitly shifting all probabilities in that state. So each update step for each time step shifts all probabilities of that state, which has some benefits because learning then doesn't just literally learn one state action value, but it affects more than just one value within your model. And finally, during inference, that part stays pretty much the same. Usually we take just the most likely action. So we take the action with the maximum likelihood. Okay, that's in short an introduction to policy gradient methods. To repeat, what are the advantages and disadvantages? First, one advantage is we're now using stochastic policies. And as discussed, that means that we have this intrinsic trade-off between exploration and exploitation. Second, we are now able to handle continuous action spaces. We need to decide what distribution class to use to parameterize this continuous action space, like typically normal distributions, but then we can handle continuous action spaces. All we need to be able to do is to compute the log probability, which is what we need to compute the update. And finally, we are now directly optimizing for our goal, which is ultimately to maximize episode returns, instead of what we did for Q Learning, where we indirectly tried to achieve this, but our optimization wasn't directly doing that. This, however, also has a few downsides. First, in this formulation that we've seen so far, and we'll come to a few improved formulations in the next block. But for the basic reinforced algorithm, this estimate of the episode return has, so the expectation of the episode return has very high variance, because basically, given that we're randomly sampling actions, our environment might behave randomly. We just will observe very good episodes, but also very bad episodes and everything in between. So potentially this is a very high variance estimate of the gradient. And so the updates might not be very precise. And second, we can, as I had mentioned this before, we can now only use on-policy samples for the policy gradient formulation. It's important that the samples that we're using for optimizations are the one that were collected by the policy that we are optimizing. So different from DQN, where we have used this replay memory and we could leverage very old observations and still improve our model. Here, we always have to collect new episodes and then perform another update, and collect new episodes again, perform another update. And this is quite sample inefficient. It means that we might train, it might take a very long time for this model to train. However, in practice, this still works surprisingly well, given these problems. And So yeah, then for the next half an hour or almost 40 minutes, I guess, we have another exercise on policy gradient methods, which you can find here, link on the website, or probably also in the chat very soon. And as always, use the QA tool if you have questions, and we'll be around to answer them.
Hi, everyone. Welcome back to the reinforcement learning for information retrieval tutorial. Hopefully you have successfully run the policy gradient exercises. So now I would like to talk about the IR applications using the reinforced Prism. So the secret to the success of reinforced is, I think, shown in the formula. But this is the key equation here for the reinforced algorithm, which is the typical policy gradient method for reinforcement learning. And we see that each step, when we need to update the model using the gradient, it could be estimated using this equation, and the R of the trajectory tau is the reward. And the key point here is that this reward does not need to be differentiable. So we see that in this equation, it is just a black box. So this implies that you can actually use this reinforced algorithm to optimize pretty much anything you would like to optimize by trial and error. And of course, this may not be the most efficient method, but this is at least could be used as the last resort. So if you have something, some objective function that could not be easily optimized using some standard supervised learning method, I think reinforced could be considered. And as Alex has explained, the idea of underlying reinforce is straightforward. So the good actions should be made more likely to happen, and bad actions should be made less likely, and that's it. So from this perspective, you could consider reinforce as a weighted version of the maximum likelihood for supervised learning or imitation learning. So in supervised learning or imitation learning, all the actions taken are good actions. Right? Whereas in reinforced, the actions that you take could be good or bad. This depends on the reward of the entire trajectory. So here, this is important that it depends on not just the current step, but the whole trajectory that involves a number of actions. Reinforce can actually be used for partially observable Markov decision processes, where you could not see all the relevant information in this state. And this is something that often occurs in practice. But the reinforced algorithm could be applied without modification. Alex has mentioned that one notable weakness of the reinforced algorithm or policy gradient in general is the high variance. But actually, this could be alleviated by using the baseline function or actor-critical methods, which would be expanded by Miguel later. So the other severe limitation of the standard reinforced algorithm is that it can only make use of the own policy data, and this could actually be removed by using a technique called off-policy correction based on importance sampling. And my colleague Murat is going to talk about it in detail at the later section of this part. Right. So first, I would like to talk about a series of papers on this topic, making use of the reinforced algorithm for learning to rank, which is a central problem of IR. So I'm actually working together with one of the authors to extend the models along this direction. And the authors come from the Chinese Academy of Science and also the Bellman University. So all these papers are talking about the usage of Markov decision processes for research problems, and the concrete reinforcement learning algorithm that they have used is just the reinforced algorithm presented by Alex. So let's look at the problem learning to rank, which we should all be familiar with, given the query and the retrieve the documents as the training data. We could use different kinds of learning to rank algorithms to learn a ranking model. So the learning algorithms could be pointwise or pairwise or listwise, but all in the end would end up as a ranking model. So when the model has been trained using the offline data, it could be deployed to perform online ranking of the documents for the queries that the model has not seen before. Right, so here the key is that issue is that there's this independence relevance assumption, and the utility of a document is independent of the utilities of other documents. So this is, or in other way, you could consider this traditional learning to rank problem as ranking through scoring and sorting. So here, in other words, we just try to use the ranking model to assign a score to each individual document in the candidate set, and then sort these documents according to the score to generate the ranked list of documents to be returned to the user. So the scores are independent of the rank, and also the each document would be scored independently. So in this way, the ranking positions of the documents would be ignored, and also it is not easy to take into account the interdependencies between documents. In contrast, if we consider this ranking problem as a sequential decision-making problem, then we could make use of reinforcement learning to address these two shortcomings or drawbacks. So, in short, the advantage of using reinforcement learning for learning to rank is to go beyond the independence relevance assumption. So using reinforcement learning algorithms, we could model the dependencies between documents and take the ranking positions of documents into account when we generate the ranked list of documents. So let's formulate the ranking of documents with respect to a query as a Markov decision process. And in this, we mimic the user's top-down browsing behavior. So given a query, the ranking model tries to find the relevant document to be returned at the first position and second position, and so on and so forth. So each step is an action that the ranking model needs to take. So the ranked document list would be generated by making this sequence of decisions. So at each step, the ranking model would need to decide which document to choose to fill the case position. So let's have a look at the entire process. So we start from the given query, right? And then the query would be represented as a vector, for example, using TF, IDF, or other embedding methods. So this query vector would be used in the ranking model, which starts from the initial state as 0. So here, X stands for the set of candidate documents. At the beginning, this refers to the entire document collection. Phi is the model parameter. And there are some the other parameters, which is to transform the query representation. Then we would use this ranking model learned by the reinforcement algorithm to calculate the policy for the given state, ST. So the optimal action in that state, AT, is going to be chosen using a softmax function. Basically, this is a probability distribution over the candidate documents. And the score of each document, right? Or in other words, the score of different actions would be measured by this, which is the representation of the document X, right? Transformed by a matrix and then multiplied with this hidden vector H that captures the user's information utility that has already been fulfilled. So we're going to look into the details later, but roughly this is the general process. And the next step is to sample the document according to the policy. So for example, at the beginning, we would use the model to determine the action to take. In other words, to choose the document at rank 1. Right. So this is the next step. We would want to calculate the reward that we have received based on the feedback from the user. So, for example, whether the user has clicked on the returned document. And more generally, we would want to use performance measure for information retrieval systems, so such as alpha DCG. So generally speaking, we would use the increment of that performance measure as the reward. So this is the alpha DCG of the step t+1 minus the alpha DCG received at the previous step t. So the increase of this performance score would be our reward signal that can be used. And remember that this kind of reward is usually not differentiable, but that's fine for the reinforced algorithm. So using that signal that we have received, the reinforced algorithm would update the model in this way. And there's these state transitions which would take place. Basically, you would remove the return document AT from the candidate set, and then move, update the state by revising the current hidden vector edge. So this would then be used to generate the updated vector list, which is one more returned document. So this is the entire process. We would do it again and again in many iterations until the entire document ranked list is going to be generated and returned back to the user. So in this way, we could model the retrieval problem as a Markov decision process. So for standard ad hoc text retrieval, we'd use the simply this the state at time t as the step t together with the document collection that we could choose the document from, or the candidate set X at that time step. So here a T would also, you could also consider T as the ranking position that you need to fill the document in the results list. The initial state at the beginning would be just 0, which is the first position to return the document, and the entire document collection as the candidate set. So each time when you have returned a document corresponding to the action AT, the state would be updated accordingly. So the reward to be received, if you are using a kind of a DCG performance measure, could be represented in this way. So this would be the increment of your DCG score by returning the document corresponding to the action AT. So the policy, as we have mentioned, could be represented just as a softmax function over the candidate set, and the scores for these documents would be measured by this parameter setter. So if you take the dot product of the setter vector and the representation of this action, supply it to the softmax function, you get the probability of choosing that action AT in the state ST. So this is our policy. And the gradient could be calculated by deriving the gradient function. That should be straightforward. So here you could consider the phi here as the relevance features determined by both the query and the document. So if we go further to perform diversified search, where you not only consider the relevance of the search results, but also the diversity of the search results, then this previous model could be further extended. So in this case, we would need to include the document list that has already been ranked. This needs to be included as part of the stage because we want to find novel documents which would cover some new information other than this information which have already been returned to the users in REDT. So here we would need to introduce a latent vector H that represents the user's perceived utility from the preceding documents. So here HD is a hidden vector. So in some sense, you could consider it as similar to the hidden vector in a recurrent neural network. So this latent vector will be continuously revised according to the documents that have already been returned to the user. And similarly, would define the initial state and the state transition would be defined accordingly. So here, this is the way that we would like to update the hidden vector for the user's perceived utility. So the reward is again just the increment of the performance measure. So for diversified search, we would like to use the performance measure such as alpha DCG. The policy is again a softmax function over the candidate set, but here we would need to include the hidden vector HT in the calculation of the probabilities for the potential action AT. So the gradient could be derived in the same way. So the details could be found in the paper. Right. Again, this is a sequential transition process. We start from the initial the query vector, and then the latent vector would be initialized by using the query vector and the random model parameter. So the state would be represented, including the initial latent vector. Then using the policy, we find the optimal document to be returned for the first position. So this is corresponds to the action A0, and this would be utilized to update the state. So this is the transition from the initial state S0 to the next state S1, and so on and so forth. So we would do it for each of these M documents to be returned in the result list until we have found the last document, the M's document. So the M-1 document. Then the iterative process will stop. Let's see an example. Consider the 3 query ruffles in the test set. So this query is ambiguous and it contains 5 subtopics. So the, for example, the subtopics could be the Raffles Hotel in Singapore, or Stanford Raffles, or organizing a raffle, and so on and so forth. So the top 5 ranked documents in the Clue 09 collection are large corpus have been listed here. So these subtopics covered by each of these documents would be shown in the squared brackets. For example, document 1 only contains 1 subtopic, the second subtopic, whereas document 2 contains 2 subtopics, 3 and 5. The search results may contain redundant information, so it is necessary for us to consider the novelty of a document given the preceding documents. So the objective for the reinforcement learning algorithm is to cover as much subtopics as possible with just a few documents. So the at step 0, the selected document would be the document with the highest score. So according to the initial model, the document D2 would be selected because it has the highest score, 1.19. So document this document D2 contains 2 subtopics, 3 and 5. So the next step, because of the selection of the document D2, right, the users have already received the some information of interest about the subtopics 3 and 5. Therefore, the ranking score of the document D4, right, would be reduced because it is also about the subtopic 5, right? So the score would be suppressed because of this redundancy of the information. In contrast, the other documents which do not contain the same subtopics would be promoted. So this indicates that the revised latent vector H1 has helped us to capture the utility provided by the returned document D2. So this makes the ranking model to focus on documents that can provide more information value to the user. So as a result, the document D5 which contains a different set of subtopics, would provide the highest value. So since it has the highest score, it will be chosen to fill the second position in the result list. And then as the result consequence of that is the updated latent vector H2, which would again help us to find the next optimal document D1, which contains the subtopic number 2. So whereas the other documents, for example, the document D3 would be considered as less relevant or less useful, because it would have covered the similar information as document D5. So in this way, we can see that the Markov decision process can effectively capture the user's perceived utility of information through its current state. And this could be used to generate a diverse ranking, which provide the maximum utility to the user. So the advantage of using reinforcement learning here is to utilize the IR measures calculated at the different ranking positions as the supervision information for training. And these IR measures, the performance measures such as alpha and DCG, could be optimized directly by so in addition, we could use a unified criterion to select the documents at each iteration. So this does not require any handcrafted features or heuristics. So it could be considered as end-to-end learning. And in the end, we could optimize the long-term return, including the diversity of the search results. So the standard reinforced algorithm would is a bit problematic because the gradient estimated according to the sampled document list is based on the absolute performance score. However, that is not desirable because this would generate a lot of the noise. The performance of the optimal ranking of different query, for example, Q2 here, for Q1 is a difficult query because there's only one relevant document, D11. So the best that the system can get is just one by putting this relevant document at the top position of the ranked list. However, for another query, Q2, which is a lot easier because it contains 4 relevant documents, although the ranking algorithm didn't do a good job by returning a non-relevant document first. The calculated absolute score of DCG at 5 is still higher than the other model. So the ideally, the reward that the algorithm receives should be based on the quality of the policy rather than being affected by the difficulty level of the given query. So this leads to the idea of this so-called pairwise policy gradient, where the relative, so it is motivated by the fact that we care a lot more about the relative goodness of a document ranking rather than the absolute scores. Right? And the comparison should be conducted between the documents for the same query. But it doesn't make much sense to compare the documents for different queries. So the high variance problem of policy gradient methods, such as reinforce, would quite often be addressed by using a baseline function. But here, due to the extremely large and sparse state space, the estimation of a good baseline function is difficult. So for example, here for each different query would probably need a different baseline. So the solution that this paper has proposed is called pairwise policy gradient. The idea is to use the inter-query pairwise comparison to guide the policy gradient algorithm. In the learning procedure, the pairwise policy gradient would repeat the process of sampling a pair of document lists starting from the same state. And inherently, this would be within the same query. So by comparing these two ranked lists in terms of their performance scores, the MDP, the reinforced model would update the model parameters. So as illustrated in this graph, we start from the initial state as 0, and then the ranking list of M documents would be generated one document at a time. So at first, would use the current policy to sample M documents. Right? So given the initial state as 0, so we would have two trajectories sampled, tau A and tau B. And then we would use the score, right, as the goodness of the for the first chosen action, and use that to update the model. And then the next step is that we would choose the one that is better among these two. So discard the other documents chosen, but just comparing these two lists, the one with the we take the action provided by the trajectory with the highest higher performance score in the end. So the trajectory with the document list with a higher reward would be chosen as the final choice for that position, the rank 1. And in this way, we would choose the different optimal documents, right, for each position. And so we follow this process, and in the end, we would sample M documents for each for the this first step. And so because we need to sample two lists, so there will be two documents sampled, and the next step would be 2 times M minus 1 samples, and so on and so forth, until in the end we just sample 2 documents. So if you add all this up, it would in total be M times M plus 1. document samples generated. So the algorithm is a variation of the reinforced algorithm, and you can prove that this algorithm is not going to introduce any bias, but compared to the vanilla reinforced algorithm, it would be guaranteed to have lower variance in the right conditions. Right. So next, I would want to talk a little bit about the reinforcement learning framework for relevance feedback, which is a work done by UMass researchers and Microsoft researchers. So again, we would need to formulate the problem as a Markov decision process first. So here, the given the query that consists of n terms, and the set of relevance feedback documents coming from real relevance feedback given by users, or the pseudo relevance feedback generated by the system. We would want to use the algorithm to optimize the evaluation function, which is the effectiveness of the retrieval model based on the given document collection. So this, the point is that this function is often not differentiable. For example, the average precision or ANTCG or alpha ANTCG, these are not differentiable. So we assume that the retrieval model is given, and just to focus on estimating the accurate query model to perform the relevance feedback. So here, R denotes the relevance feedback model with the parameter set omega. So Q is the given query, F is the set of feedback documents, and the C is the document collection. The existing feedback methods do not directly optimize this objective because that is difficult. So usually they're based on some heuristics. So here, if we formulate the relevance feedback problem as a Markov decision process, the environment would consist of the document collection and the retrieval model. The agent is the query model that expands the query and reweights the query terms. So in other words, we want to add and also reweight the terms to to represent the query better. The state would include the query, the feedback document set, the document collection, and the current model parameters for relevance feedback. So the action here is to sample k terms from the updated query model distribution learned by our reinforced algorithm. So here, because we want to have k different terms, so we can sample without a replacement. And then these sampled k terms would be normalized. So we, because in this direction, if we want to sort of present it as a distribution, would renormalize it, the probabilities in this subset of k terms. And then this distribution would be interpolated with the original query distribution, the original query model, for example, estimated using maximum likelihood estimation. So the reward, as I mentioned, again, could simply be considered as the increment of the performance measure. So the policy network architecture for the reinforced algorithm is again using a softmax operator. So the a single model is going to be trained to take information related to a candidate feedback term as input and produce a feedback weight So the key information here is that you want to calculate the score, which is the feedback weight for each of these candidate feedback term, W. And this score would be calculated by using a neural network with multiple components. So they use a component-based architecture so that they could consider different aspects of the feedback term. So they could here they choose L different aspects, each being represented as a subnetwork, and then they would aggregate these L representations together. And finally, all these representations would be aggregated over all the feedback documents. So in the end, you have a big network to generate the scores and for each given candidate term W. So here, in my opinion, these different components are sort of different. These kind of multiple heads in, for example, the transformer architecture. So you could just randomly initialize each of these components, and hopefully they would be able to learn different aspects of the given candidate term W for Curie expansion. And this has been shown to work well. So for the Curie dinosaur, you can see that this model works better than the traditional model IM3 for relevance feedback using TF-IDF weights. So this model IML is using the MAP as the performance measure, and the training algorithm is the reinforcement algorithm. We see that it would return most relevant terms to different kinds of dinosaurs to supplement the given query. And it could also be used, adapted easily for different performance measures, such as alpha and DCG that captures the diversity. So if you change the performance measure from MAP to alpha and DCG at 20, then you see that for some queries which are ambiguous, the reinforcement algorithm using alpha and DCG would be able to find a diverse set of terms that covers different subtopics for the relevance feedback. So switching the performance measure is straightforward and easy. Okay, so that's I think the time for us to take a break. I'm sorry that I've run over time, so please do take a coffee break of 15 minutes. Then we are going to do that later. So let me. Do we have time for the? Let's. Sorry. Shall we talk about the? I think. Yeah. Let me see if I can quickly finish this paper called IR game, which is also an application of the reinforcement algorithm, and see how much time I can give to my colleague Murat. So we have discussed the usage of the reinforcement algorithm for length to rank and relevance feedback, and so this is a model called IR again. that I have been involved. It is a work done by my clinical friends and UCL, Shanghai Jiao Tong University, and also Alibaba and Tianjin University. So roughly speaking, this is the idea to combine the two schools of information retrieval thinking, the generative models and the descriptive models. So they each have their pros and cons. Using the so-called generative adversarial networks, okay, we could take advantage of both. So here we could use the generative model to learn to fit the relevance distribution of the documents by the signal from the descriptive model. And on the other hand, the descriptive model is able to exploit the unlabeled data selected by the generative model to achieve a beta estimation for document ranking. Now, so here we don't want to go into the details because that's not directly related to reinforcement learning. The point that I would like to mention is that we could use the reinforcement algorithm for the as the generative retrieval model. So here the we could so this is not straightforward because the retrieval of documents is discrete a set of discrete decisions, right? So therefore it is not straightforward to use backpropagation to update the model as in the standard generative adversarial network. But that's we could make use of the policy gradient method. So as I've said, if it is difficult to optimize some utility function using the standard supervised learning method, then quite often we could use policy gradient instead. So because this is very general. So in IR again, you could use the reward term, the signals generated by the descriptive model to update the generative retrieval model by the reinforced algorithm. So here we are see that you are actually making use of the reinforced algorithm by sampling the documents from the document collection. Right. So the you have already seen this derivation of the policy gradient, and the key point here is that for this given reward function, we could optimize it through Monte Carlo sampling from the current distribution. So this could be estimated by through the sampled documents, and in that way we could make use of the generative adversarial networks to unify the generative retrieval models and the descriptive retrieval models to take advantage of both. And the key innovation here that enables this unification is the usage of the reinforced algorithm to overcome the difficulties of optimizing discrete decision making. Right. So I have finished my part of the presentation, I'm not sure whether Murat would have enough time to talk about the off-policy correction of the reinforced algorithm. So Murat?
Hi, do you see my screen?
Yes.
Yeah, I can continue from this point, or I can start after the coffee break. Both works for me. Let me quickly wrap up this paper before the coffee break. I think I can do that. So this paper is from Google Research, and it's about YouTube recommender system. The title of the paper is Tab K of Policy Correction for a Reinforced Recommender Systems. Let's quickly talk about the motivation. Industrial recommender systems deals with extremely large action spaces and large number of users. In YouTube case, this means we have millions of videos, and we want to, each action in our reinforcement learning agent is actually recommending one video. So we are talking about huge amount of actions in the action space. Huge quantities of log implicit feedback, such as user clicks or develop time, also available for learning in such big systems. However, learning from the logged feedback is subject to biases caused by only observing feedback on recommendations selected by the previous versions of the recommender. So we have a lot of feedback and traces maybe, but these traces are coming from the previous versions of the recommender systems, or even totally different recommendation engines. So this paper addresses such a bias in a production top K recommender system at YouTube using policy gradient algorithm reinforce. The nice part about this paper is actually the proposed approach in the paper has led to the largest single launch improvement in the YouTube for 2 years. YouTube recommender systems has two levels. In the first level, we have millions of videos, and we reduce the number to hundreds. So this stage is called candidate generation. After candidate generation, we do ranking. The approach proposed in the paper is about candidate generation, and we use reinforced algorithm. Let's talk about the parameter update in reinforced algorithm. As my colleague Alex mentioned, the parameter update is done through the gradient of the expected return. And then this expected gradient of expected return using log trick is reduced to expectation of gradient of weighted log likelihoods. Here, the weights are the returns. However, this formulation leads to high variance. Even though it's unbiased estimate of the gradient here, it has high variance because this return has many components. In order to reduce the variance, we use discounted future reward. It means that, so we don't take the return of the episode, but for at each time step, we only take the future rewards and we weight it using gamma. In our case, S is the state, representing the state of the user, and A represents the video we propose to the user. And the reward is can be considered as the time spent on the video, the comments and the likes left for the video. We start with an initial user state, and we use a recurrent neural network to update the user state using the embeddings of the videos watched and other feedback about the user, about the videos. So this is a very simple view of what is happening. However, in the literature, it's shown that considering the context is making recommender system provide better recommendations. So in this paper also we add context to the videos to update user state. This is the actual architecture from the paper. What happens here is we have video embeddings, we attach context, and the context may contain the device type, the page embedding, and so on, the page of the video, I mean. Then we update the state of the user based on this information, and also attaching here also the label context, which represents the context related to the device and the query of the user. Then we have here two softmax functions. The first softmax function here represents actually the target policy, the policy we are trying to learn. And using this softmax function, we are choosing a video among possible candidates. The second softmax function is, on the other hand, used for a different purpose. It is used to model the behavior policy. I will talk about behavior policy very, very shortly. One problem with this context is the large action space. So using softmax, calculating exact softmax function is not feasible. That's why we do approximations here. For training, we use sample softmax because it's easy to do it. On the other hand, during inference, it is hard to do sample softmax. So we also use fast nearest neighbor lookup before sampling. So this makes us to calculate an approximate softmax easily. Now let's talk about the actual contribution of the paper. A naive policy gradient estimator is no longer unbiased here, as the gradient requires sampling trajectories from the updated policy pi, while the trajectories we collected were drawn from a combination of historical policies. So what we have actually logs from the previous versions of the recommender system. So we cannot anymore use the policy gradient formula. We need to make some corrections on that. The actual problem here is the target policy is different from the behavior policy where we used to train our reinforcement learning agent. It's mentioned before, but let's shortly mention it here. On policy means that the agent actually, agent learned and the agent interacting with the environment is the same. In the case of policy learning, the agent learned and the agent interacting with the environment is different. Off-policy learning has a lot of advantages because it allows us to learn using the experience of other agents. We don't need to sample the environment by rolling out episodes anymore. We can exploit the existing episodes and logs for training. In the literature, studied actually how to tune on-policy for off-policy learning. One common approach is using importance sampling. Let's slightly talk about importance sampling here. Let's consider that we want to calculate the expectation of function f of x based on a distribution p. So we sample x from distribution p and take the average of those samples for a Monte Carlo estimate of the expectation. However, the problem is we cannot assume that we don't have samples from p, but we have samples from q. Maybe it's cheaper to sample from q than p. So how we can actually calculate an expectation over distribution p using the samples from q? One approach is simply multiplying and dividing to density q of x, and calculate this calculation leads to an expectation over the distribution q. The main difference is we have here an importance weight. With this importance weight, actually, we can accurately estimate the expectation of f of x with over the probability p. So if we use the same idea in this setting, we have this formulation. So the original reinforced algorithm now has a weight. With this weight, now we can calculate the expectation over the behavior policy. We don't have to do it over the target policy anymore. So this allows us to have a sample efficient training of our target policy. Let's look at some more details. So this is the original on-policy reinforced algorithm. As you see, the expectation is calculated over the target policy pi theta. So with important sampling now, we can use the behavior policy. So behavior policy, remember, represents the feedbacks logged over time using different recommender systems. So it allows us to use the same data again and again to train new target policies. However, this weight here, the ratio of the likelihoods here, has a high variance. To avoid this, we ignore the terms after time t, and we take the first order approximation. Just move on. Okay, so if we go back to the architecture, I can now talk about just a second. Okay. I can now talk about the second softmax here. The second softmax is used to learn the behavior policy. So this is a one-layer neural network with softmax output, and it is actually only used to predict the probability of actions using the behavior policy. Because if you look at the formulas, in these formulas, we need the ratio of the probabilities of actions given the states. So in order to calculate this this probability of having action A given state through the behavior policy, we need this softmax. Of course, to avoid any problem in the target network, we block the gradient. So we only train this layer. The paper is evaluated through a number of simulations, also live experiments. I will show you here one of the simulations, which is quite interesting. In the simulation, there are 10 items indexed from 1 to 10, and the reward of each one is equal to its index. So the highest reward is given to the item in index 10. The policy pi learned without off-policy correction when behavior policy is this would be skewed to forward the actions with least reward, because if you look at the behavior policy, it favors the actions with least index. If we train our target policy without policy correction, we have these probability distributions over actions. As you see, it's far from being optimal. On the other hand, with off-policy correction, as you see, the agent with the target policy picks the item at the last index, almost always. So it is much more closer to the optimal policy. So this shows the advantage of the policy correction and including important sampling. However, recommender systems doesn't provide only one item, right? They provide k items on a page, so the recommendation usually more than one. So how we can extend this approach for top k recommendations? The paper here takes a simple approach. Instead of proposing a set, it does a sequential draws from the same policy. So this way, the problems becomes more tractable. What happens is the items of an action set A is generated by independent sampling each item video according to the softmax policy, and then we duplicate because there is no guarantee that each item is unique. But it isn't a problem because we have millions of videos. It's very unlikely that we see the same item many times in this set. So then what we have is the gradient update rule can be adopted for a set of recommendations by replacing pi with alpha theta. So alpha theta is a deterministic function which is calculated as follows. If you look at closely, you will see that this is the probability that the action A is not selected as any of these k picks. So 1 minus this probability indicates the probability that this action is selected as one of these k items. So what we do is very straightforward. We replace the original correction with this one, where we only replace the pi theta with alpha theta. If you do the math, you will reduce this formula into this formula. As you see, the only difference here is this term. So we add an additional weight. Now let's look at this weight. This additional multiplier needs to be added to the original off-policy correction factors. And if we calculate this, we will have this result. So this is the derivative of this ratio. So this is the ratio of derivatives here. If you look at closely, you will see that when the desired item has a small mass in the policy, the top K correction more aggressively pushes up its likelihood than the standard correction. Because if the desired item here has a probability close to 0, this term gets close to 1. And when you multiply it with K, you have a weight greater than 1. On the other hand, if the item desired already has a mass, a probability mass high enough, this term will gets closer to the 0. So it will allow the policy to focus on the desirable elements, which has already small probability mass. I think this is very interesting. If you look at the simulations here, you'll see what I mean. In this simulation, there are 10 items. And the first and second items has the highest reward. The first one has reward 10, second one has a reward 9. And the remaining ones has much smaller reward, all equal to 1. If we use only top 1 correction, our target policy becomes this one. So our policy has high probability of picking the first item, and all other items has equally small probabilities. So if we need to recommend a second item, we probably pick it randomly and probably will not pick the right one. On the other hand, with top K correction, the probability of the second item, which is the best second item we can propose, is pushed up, and it gets greater and closer to the probability of the first item. So we have a better chance of recommending 2 desirable items with this top K correction. And this way I can wrap up. So in this section, we have seen search as Markov decision process. We look at a number of papers. Dell described a number of papers related to learning to rank, relevance feedback, and argument generator. Also, we have seen different tips and tricks, such as pairwise policy gradient, of policy correction, and top K correction. I hope these reviews of these papers and these tips and tricks will help you to relate information retrieval with the reinforcement learning approaches we have described here. Thank you very much. Now it's time for a break, a coffee break.
Okay, so I'm going to get started on the next section, and actually I'll be doing the next 2 sections. So my name is Miguel, and we're going to spend the next 20 to 30 minutes talking about actor critics. And after that, we'll also be doing an outlook, kind of looking forward to extensions of some of the areas of deep reinforcement learning that we've covered so far. But first, yes, let's talk about actor critics. So actor critics, as was hinted previously by Alex and a few of my other co-presenters, is a combination of both Q learning and specifically DQN, as well as policy gradient. So to motivate this, let's first take a look at our policy gradient theorem again. So here we have a gradient over the expectation of the reward of our trajectories. And as we saw previously, we can convert this to an expectation over an expression involving gradients. But there's 2 problems with this, and this is going to motivate the usage of actor critics. So the first problem we have is that it's actually quite data inefficient, and Alex mentioned this previously. So with this approach here, what we need to do is we need to collect at least 1, if not multiple, episode rollouts in order to do our updates. And compared to DQN, this is a big downside. In DQN, we were able to update at every single time step. So obviously, we'd like to improve on that and maybe go back to a version where we could do this per time step instead of either across at least one rollout or multiple rollouts. The other problem with reinforce is that we have this issue of imprecise reward assignment. So if we look at our expression again, we see that we're scaling the gradient of the log probabilities here in the inside expression with this constant reward term, the reward for the trajectory. So all the actions within an episode get the same return. And intuitively, this doesn't feel quite right. So if we think about it, later time steps can actually be influenced by early rewards. So we'd ideally, we localize our rewards a bit more. We do a better job of assigning this reward to the correct time step. So with Actor Critic, we're going to address both of these issues. Okay, so the first thing we're going to do is we're going to take our reward, our straightforward reward scaling, and we're going to replace it with reward to go. We actually saw this already in the exercises. And just to reiterate, basically with reward to go, you're only going to, at each time step, you're only going to consider the rewards that occur in the future. So this solves the second problem where the reward assignment isn't quite right. Right, and then after doing some maths, and here, especially with Actor Critic, there's a lot of derivations, and we have links to proofs for those on the website as well as at the end of the slide. So I encourage you to take a look at those, but you'll just have to trust me on this one for now. If you take the expectation over the reward to go, it gives you the state action value, or the Q value for current state action pair. So given that the expectation over this reward to go is simply this Q value, instead of using the reward to go, why don't we just use the Q value as we did in Q Learning? And this gets us to our first version of Actor Critic, which we might also refer to as Q Actor Critic, where we've taken this constant reward scaling, we've replaced it with reward to go, and then we've actually replaced it with a Q function that we can then learn. Okay, so to summarize, we have our new expression. So our gradient over expected value of returns now becomes an expectation over two parts, right? So we have two models now. We have our policy in blue here, which we train using policy gradient. And now we have, and this is called the actor. And then we now also have our critic. And this critic is this Q value function, which we can approximate using TD learning in the same way that we did with Q learning. So of course, we now have the advantages that we mentioned earlier. We now can update at every time step. We actually don't need full rollouts anymore because we now have this Q function where we used to have the reward for the whole episode. And of course, this makes it more data efficient. I guess one thing to note, though, is that does introduce some potential problems because now we're training two models simultaneously, right? So this could make things a bit more complicated, and we'll go a bit more into detail on that towards the end of the Actor Critic section and discuss the consequences of now having two models to train simultaneously. Okay, so if there's an Actor Critic 1, then of course there's an Actor Critic 2. So something that we can show, and again, I'm going to have to direct you to some of the links at the end to show this more formally, but you'll just have to take my word for it for now. We can show that for any state dependent baseline function, which we denote here as B, the expectation of this baseline function times the gradient of the log probability of our policy is actually going to be 0. So I guess important to note here as well that this baseline function should only depend on the state and not depend on the action. And of course, this means that this doesn't actually mean that the baseline function has to be 0. It could be 0, but really that it's the expectation of this baseline function times the gradient of the log probabilities that is 0. Okay, so given that we have this first expression on the top involving the baseline function, since that expectation is 0, we can just take that expression and subtract it from the expression we were using in the policy gradient theorem, which is what we have right here. And since, of course, we're just subtracting 0, nothing happens, and it's fine to do this. So if we look at this expression in a bit more detail now, so we have the expectation over the sum of every time steps, and now we're scaling the gradient of our log probabilities with this new term, right? So we have the reward to go minus our baseline function. So the important thing to note here is, although the expectation doesn't change, right? It's mean preserving. If we correctly select this baseline function, what this can do is this actually can be variance reducing. And as Alex mentioned in his section on policy gradient does have this issue where the updates can be very high variance. So this is actually one way of addressing that. We're using this baseline function to actually reduce the variance. And actually, it can be further be shown that the optimal choice for this baseline function, with respect to this variance reduction, is to actually just use our state value function, that we have v, and we've seen this before, right? This is just our expected value moving forward given a current state. So the final formulation here of this actor critic 2 is, once again, we have this expectation over all these time steps, and then we're scaling the gradient of our log probabilities with the reward to go minus this state value function, which thus causes the updates to have a much lower variance. And we'll give a bit more of an intuition on that in a couple slides. Okay, so to summarize, actor critic 2, the two new terms we have here in green and blue. So our actor is still the same as for actor critic 1, and as in policy gradient, we still have this blue actor term, which we can update using the policy gradient formulation. And now we've introduced this state value function v, and we can train this in the same way we did for the state action value function, these Qs, these Q values we were seeing previously. We can train this value function in the same way. Right, and the advantage here, as I mentioned, is that because we're using this state value function, and it's optimal with respect to variance reduction, our gradient estimator is now much lower variance in our updates. And the other advantage here is it actually gives a bit of a nice intuition with regards to relative versus absolute perspective. So previously, when we were just looking at either the total reward or the reward to go, we had this view on how we were supposed to perform that was absolute, right? We were just taking the absolute reward. But now we can look at it as a relative reward. So this v, this state value function, is how well the expected reward for the current state. And this reward to go is the actual reward. So if we do better than expected, if our true reward is higher than the expected reward, then we have a positive update. But if our true value is lower than our expected reward, we have this negative update. So now we have this relative perspective on the update. Are we doing better than we expect, or are we doing worse than we expect? And then we update our policy accordingly. Okay, so as I mentioned a couple of slides ago, I'd asked you to kind of take my word on the fact that using a baseline was, in fact, variance reducing. So here I'm going to try to give a bit of an intuition on why that is, in fact, the case, because it might not immediately be quite obvious, but hopefully this example demonstrates that. So first, let's assume we have a distribution over 3 actions for a given state. So let's just call our state S, as we see here, and we have 3 actions. We have action 1, action 2, action 3, and they all happen with some probability, 0.2, 0.5, 0.3 respectively. And in addition, we have Q values for all these state action pairs. So we have for state S, action 1, the Q value 6, for action 2, it's 7, and for action 3, it's 8. So let's now first look at our estimator without this baseline. So without this baseline, we just have our Q value here, which scales the gradient of the log probabilities. And if we expand this using what we've written above, we get this update expression here. So we have 0.2 times, which is the probability of our action. So 0.2 times 6, which is the Q value of action, times the gradient in the log probability, and so on and so forth for actions 2 and 3. And now we compare that to what it looks like, so with the baseline. So if we assume that our baseline is 7, which is more or less what it would be given the Q values up here, right? So if the Q values are 6, 7, 8, we would expect that the state value function is going to be about 7. So if we just assume it's 7 for now, and we plug that into our equation where we're subtracting the baseline, we end up with this expression down here, right? So we have negative 0.2 times the gradient of the log probability for action 1, and 0.3 times the gradient of the log probability for action 3. So why is this lower variance? Well, let's take a look at the without baseline version, right? So the gradient of our log probabilities, even if they're small here, they're actually going to be scaled up by the Q values, the 6 or the 7 or this 8, before being multiplied by the distribution as well. But if the gradient of the log probabilities are small and we look at the version with the baseline, they're going to get scaled down because we have actually reduced the impact of these Q values by using that baseline function. And then once again, this kind of gives us this perspective of relative versus absolute, right? So in the version without the baseline, we were out looking at the absolute impact because we were just looking at the Q values. But the version with the baseline, we're subtracting what we expect to happen. We're subtracting this state value function. And so now we have this relative perspective, and thus the variance is much, much, much smaller. So hopefully this kind of gives an intuition as why this reduces the variance, but it's still mean preserving for the gradient estimator. Okay, so to summarize, we have actor critic 1, also known as potentially Q actor critic, where we first replaced it with reward to go, and then we replaced it with our Q value function. And then we have actor critic 2, where we've then used our baseline function, this V, this state value function, which helps us reduce the variance. This is also known actually as advantage actor critic, and that's because this term here, where we have the reward to go minus the state value function, is actually seen as an advantage, right? This once again, this comes back to the intuition about this is now a relative change versus an absolute. So the reward minus the state value function is an advantage, right? And so that's advantage actor critic or A2C. And finally, we can actually, combine actor critic 1 and actor critic 2 in this final formulation, which is sometimes also referred to as A2C, but here we're going to choose to call it TD actor critic. So what we've done here is, instead of using the reward to go, we're actually just going to use the state value function for the next time step, and then scale that with our discount factor and add the reward for the current action. So this kind of gives us the best of the both worlds, right? So now we can update at every time step because we don't depend on the reward to go, and we only depend on these state value function, which we can train like Q learning, so we can train them at every time step. But we also get the big variance reduction from using this baseline function. Right, so this kind of solves both the problems we were seeing at the beginning with reinforce. So what does this actually look like in practice? Well, what we can do is we can take our actor and we can take our critic, and we can randomly initialize them at the beginning of training. But what's important to note is how they actually interact with each other in the environment. So we have this little diagram at the bottom, and we're just going to kind of walk through it to see how that happens, right? So our critic, pardon me, the actor. So the actor interacts with the environment through the actions, but it can only observe the reward indirectly through the critic, right? So the reward landscape is propagated through the critic to the actor. So the actor really depends on the critic to get that value estimate from the reward from the environment. On the other hand, the critic can't interact directly with the environment, right? It needs to pass its value estimate through the actor, and then the actor performs an action, which then interacts with the environment. So the training data for both the actor and the critic is actually determined by only the actor's decisions, right? So you have you have this interplay between the actor and the critic, and there's kind of this dependency, which can make things tricky when training them both together. So what does that look like in practice? Well, let's take the training kind of to an extreme in both cases, and that can kind of give a bit of an intuition on the concerns that we might have here when training both models simultaneously. So let's say we only focus on training the actor first, right? So we're only training the actor. And what that means is if the actor gets very certain about what it's doing, then it's going to stop collecting a very, very varied experience, right? It's going to keep performing the same actions over and over and over again, right? And since the training data from the critic comes fully from the actor, then the training data is going to be not varied, and we're going to get a very poor critic, right? The critic's going to have very poor training data, and that's just going to perform very poorly if the actor gets too certain too early on. On the other hand, if we only train the critic, that means that in the, at least in the advantage actor critic version, we're going to get 0 advantage, right? So that if we're very good at predicting that state value function is going to be identical to the reward to go, right? Because our expectation is going to be super good. So we're going to match up very well with what actually happens. And so we're actually going to get a 0 there, which caused the updates to be 0. So this is, of course, desired behavior if the task is solved, right? If the task is solved, we want to be very accurate with our critic, and we want that update to kind of converge to 0, that advantage to converge to 0. But it's very undesirable if that happens too early, right? So if the critic gets too sure too early about what's going to happen, if it gets too good at it, then the actor doesn't get any good training signal. So really that kind of points to the fact that you can't have one of these performing too much better than the other one, and they really need to evolve in tandem, right? You need to train them simultaneously. So in practice, the basic idea of just training them at the same time can work quite well, but there's a lot of variations that exist out there. So for example, you could kind of at the beginning only train the critic until it has a sufficient accuracy, and then start training the actor. And that can kind of help stabilize the training at the beginning if the training signals are kind of too noisy if you're training them fully simultaneously. Also in practice, it's quite common to update the critic at a higher frequency than the actor as well. And both these are just kind of heuristics because they can help the actor and the critic behave, help the training of the actor and the critic behave better. So really all of this to say that, actor critic can be super powerful and it can perform really well, and it gives you kind of the benefits of policy gradient as well as DQN, but you need to get this balance right. It introduces some additional complexities. Okay, so we do have an exercise for actor critic as well. The link is here. I'll drop it in the chat as well. It's going to work through a lot of the things we've seen previously in the previous 2 exercises for TQL and DQN, but it, of course, has the actor critic implementations, and I think we also have a new environment. I think perhaps it's Pendulum. And once again, feel free to drop any questions in the chat, or, of course, just raise your hand. We can answer questions there as well. And then we're going to go with this exercise until 4:30, for another 10 minutes. So we're going to go for 10 minutes with this exercise. And at 4:15, I'm going to pick up with the next section, which is the outlook. Thank you. Okay, so it's 4:15. I'm going to get started on the next section. Just a quick note, the actor critic exercise, it doesn't have any fill in the blank sections. It's much more to kind of play with the parameters and see the implementations and see how, changing those parameters affects the training. So don't worry if you didn't get a chance to get through all of it. But in the 10 minutes that I gave you, it'll be online for the foreseeable future. So you can always play with it after. And yeah, if you have any questions, just feel free to drop them in the chat, even if it's during the next section, and we'll try to get to it as soon as possible. Okay, so the last section we'd like to talk about today is what we're calling the outlook section. So there's a lot of stuff we weren't able to cover today, of course, because reinforcement learning is a very large field. And in this section, we're just going to try to provide a glimpse to some of the extensions or active areas of research and some open questions that we think are of interest. And I'm also going to provide some links to some papers in here. So if you're interested in any of these extensions, please feel free to check those out after today. Yeah, hopefully it gets you excited to look at some of the extensions in deep reinforcement learning that we didn't really get to cover today. Okay, so the first area of extension that I like to cover, we're going to call it data collection. So as we've seen in the exercises, and hopefully as you've realized when you've been playing with them, training these agents can be quite time consuming, especially because you are both interacting with the environment and training simultaneously. So this kind of data collection can very quickly become a bottleneck, right? So how can we improve this? Well, if we're working with a simulated environment, we could separate the data collection from the training, right? So an obvious way of doing this is to parallelize our environment interaction. So we could have multiple copies of agents and multiple copies of the environments, all gathering data in parallel, right? So let's say you have hundreds, you could have thousands of them. And then once they've gathered this data, then you could pass it to a separate system which actually performs the training. And this lets us kind of parallelize not only across different agents for the interactions, but also parallelize the training. We can train at the same time as we're gathering data. And of course, this also potentially lets us gather more data in the same amount of time. And taking these expectations over larger amounts of data can, will most likely yield better updates because they're going to be less biased. Of course, this does also introduce some complications. There's no free lunch in this world, so it does introduce a bunch of complications around communication, right? So you need to communicate all the training data back to a central server, and then when you do the training, you need to take those parameter updates and those new copies of those agents, and then redistribute those to all the nodes which are doing the interactions with the environment. So there's all these kind of complexities around synchronizing all these parts and communicating the data that this does introduce. Another approach to this, instead of parallelizing across collecting the data, you could actually fully distribute the model training. And how this works is you would potentially have multiple copies of the agents on different machines, and all of those would be interacting with the environment, but they would also be performing, also gathering the updates. And then what we do is we take those updates and send them back to a central parameter server, and we can apply those gradient updates, and then the central parameter server can then propagate those parameters out again. And both of these papers that I have here talk about really kind of scaling up deep reinforcement learning and kind of letting you deal with these approach where you have kind of asynchronous training. And one you might have heard of already if you've looked into deep RL is asynchronous actor critic, or A3C, which is a clever naming that they've added on top of here. And once again, of course, with either of these approaches, you do have this extra burden of worrying about how you're going to communicate and how you're going to synchronize all these pieces, although it does help you with the collection. And it also only works if you have a simulation of the environment. This isn't going to work if you're in a real world scenario. Another extension is learning from demonstration. So let's say you already have data of an agent interacting with the environment, and you'd like to leverage that when training your agent using reinforcement learning. So how would we do that? Well, one way of doing it is called imitation learning. And what we do in imitation learning is very simply you train the policy to imitate what it's already seen in demonstrations. So for example, let's say you have an expert who's driven a car. Well, you could use those demonstrations of that expert driving the car and then train your policy to imitate that ideal policy. And this in and of itself, imitation learning is actually a huge subdomain. So there's a lot of work on here and different approaches on doing this. Another approach, and also its own kind of big subdomain, is called inverse reinforcement learning. So in inverse reinforcement learning, instead of trying to imitate the policy, what you're actually trying to do is learn a reward function. So given a collection of data of an agent interacting with the environment, you're actually just going to try to learn that reward function. And then when you're training your policy, you're going to use that learned reward function to train your policy. And this can kind of be seen as a way of learning the reward shaping. So we saw this reward shaping in DQN and in policy gradient and the exercises. So one way of kind of looking at this inverse reinforcement learning is you're actually learning this reward function. You're seeing what it should look like based on all this data we've gathered. So both of these approaches can be really useful when you're working with real world problems. So for example, autonomous vehicles, it might not be feasible for your car to just crash all over the place at the beginning if you're just letting it interact with the world. But, we have a lot of data about either experts driving cars or people driving cars. And we can, using these approaches, imitation learning and inverse reinforcement learning, we can leverage that data so that we don't need to run an untrained agent in the real world. We can make use of this kind of off policy data to train our agent and have it perform in a good state before we kind of unleash it on the road. Another extension is around internal state. So far, all the agents and the policies that we've looked at have been reactive. So the way that we've implemented, they can't really remember what they've done in the past. All they're doing is they get a state and they just look at that state and they're then going to decide what action to do. But intuitively, it kind of makes sense that we'd maybe want to have some understanding, and by we, I mean the agent. The agent would want some sort of understanding of what it's done before, the states it's seen or the actions it's done. So imbuing this agent with some type of memory could actually be quite useful for it to perform better in these environments. It might allow it to do some types of more kind of long-term sophisticated planning and have kind of this evolving decision making instead of dealing with everything reactively, right? Instead of just being like, oh, state action, it could be like, okay, I've done all these actions and I've seen all these states in the past. Now I can make a much more informed decision of what I should be doing. So if we're in, dealing with a world of deep learning, an obvious candidate for this would be to use RNNs, potentially long short-term memory, and kind of use those to give our models an ability to remember stuff and plan over longer time periods. That being said, although this has this benefit of potentially allowing for long-term planning, it does complicate the training a lot. So when we talked about DQN and policy gradient in the past, we were able to assume that each time step was essentially independent. But now that we have to worry about internal state, we have to carry that state time step to time step when we're doing training, right? So for example, one of the add-ons to DQN is that we were able to use these replay buffers to kind of store all this past experience and then sample from it to do our training. That wouldn't really be possible anymore, or not trivially possible when we're using a concept of internal state, right? Because we need that internal state to be in the right position when we're doing the training in order for that training to be meaningful. So having this memory in the agent does make the algorithmic side of the training quite a bit more complicated. So just something to bear in mind. Another extension we're calling predicting the future. So what does that mean? So one thing that might be useful for agents to do is, instead of just being trying to get the maximum reward, is to have the ability to reason about what the future might look like, right? We could ask our agent to have an understanding of either what the next state would look like, or maybe what the states will look like 10 time steps from now. And the nice thing about this is it can provide some sort of additional training signal, right? If we kind of have this auxiliary loss based on the agent's prediction of the future, it provides a training signal, and that can be really useful when the rewards are sparse. So for example, in Frozen Lake, if we don't provide a reward for falling in the hole, it only gets a reward when it finds the Frisbee disc. That reward can be quite sparse, right? The agent's not going to find the Frisbee all the time, so it doesn't get a lot of training signal. So what we could do is we could add this auxiliary reward about being able to correctly reason about what the next state will look like. And that can have this nice synergetic effect in helping it kind of learn this good policy. The other cool thing you can do when you give the agent the ability to reason about the future is you can kind of build in this concept of curiosity or surprise. And this is actually, again, this idea of curiosity and like surprise or like intrinsic motivation is actually, again, like a whole subfield of reinforcement learning. There's a lot of work around on this. And what I mean by curiosity is that, let's say that and by I, again, the agent, let's say that the agent has some sort of prediction of what the next time step will look like, but that prediction is very wrong, right? So if that prediction is very wrong, we can then reward the agent for actually visiting time steps that it's actually poorly able to predict. We kind of give it a curiosity, right? The agent doesn't have a good understanding of what's going to happen, so it's going to be curious about what it in fact will happen, so then it goes visits those time steps. And this gives kind of a much more meaningful understanding of exploration versus exploitation. So recall that in Q learning, we did our exploration versus exploitation by doing an epsilon greedy approach, which, although it works well, is not super meaningful. It's kind of this heuristic. In policy gradient, it's a bit better because we have this stochastic policy that we're able to sample from. But having this idea of curiosity or surprise is this kind of much more meaningful way about reasoning of exploration versus exploitation, right? If the agent isn't able to predict well what's going to happen in the next time step, then maybe that agent should be moving towards that state to see what would actually happen, right? It explores stuff that's unknown, and then stuff that is known that it does a very good job of understanding what's going to happen. It can maybe work with that less. And then you can kind of balance much better the agent behaving safe or, wanting to explore a lot more based on its ability to reason about what the next time step should look like. The other thing that can be added on for reinforcement learning is goal parameterized policies. So in the real world, a lot of times you're not going to be working with like a single goal, right? So let's imagine that we have an embodied agent who's interacting in a 3D environment where there's all these different shapes, right? So we want to be able to tell the agent, okay, go pick up the red cube or go pick up the green sphere. So having this ability to have one agent able to deal with multiple different objectives is potentially quite interesting, right? So you could potentially parameterize the policies with the goals, and so that the goal is incorporated as part of the policy. And this also, it can be useful if you're kind of dealing with the agent as part of like a larger control system, right? The larger control system doesn't want it just wants to be able to tell the agent what to do, and it doesn't actually want to necessarily understand how the agent's doing it, but having the agent be able to understand these different goals in that case can be quite useful. And the last extension that I would like to talk about today is model-based influences. So as you might recall, right at the beginning of the day, John presented on kind of two big subdivisions of reinforcement learning. We had the model-based approaches where you're trying to learn a model of the world and then use that model in order to do planning. And then, of course, we have model free, where we don't try to learn a model of the world, and we're just trying to learn a policy or a value function that kind of allows us to interact with the environment optimally. And then for the rest of the day, we mostly talked about model-free approaches. And the big reason for that is because in the last 5 years or so, most of the literature, and especially when focusing on deep reinforcement learning, has been on model-free. A lot of the advances have been there as well. But that being said, there are obvious appeals to using model-based approaches, or at least using some parts of model-based approaches if it's available. If we have an understanding of how the world works, it seems kind of silly not to use that understanding in order to improve our training. So there's been work in kind of using these model-based approaches and using them to improve our model-free methods. So one area of work on this, and which really kind of takes it to an extreme, is essentially what's called world models. And what these world models are is essentially you learn a model of the world, and then you use the model of that world to train the agent, and the agent only, the model-free agent only interacts with that world model and doesn't actually see the real world until test time. And there's actually been some quite surprising results on this. And one of the big advantages, of course, is if your world model is simpler than the real world, which it's likely to be, but still captures a lot of the salient features, then it might be a lot faster to train your agent on these simulated world models than, for example, having it interact with the real world. And there are some tie-ins here to my previous point about predicting the future. In predicting the future, we were learning, we were using our ability to predict the future as like an additional training signal. And here we're using our simplified world models once again as potentially like this additional training signal. Okay, so to summarize, we've talked about a few different extensions to reinforcement learning, I guess specifically deep reinforcement learning. We talked about data collection, learning from demonstrations, internal states, predicting the future, goal parameterized policies, and model-based influences. That being said, this list is very far from complete. There's a lot of other areas that are super interesting. This is just really trying to provide a glimpse of what's out there, and hopefully getting you to start asking questions and to start digging. There's a lot of avenues here we just weren't able to cover. This is a super active field, and there's lots of research happening all the time. And it's actually quite hard to stay on top of all the latest literature. But we have a lot of links again on the website, and as well as the links on the slide. And I invite you to check those out on your own time, and see what areas interest you and pique your interest. Yeah, okay, and one other logistical note. So here at the Blue Prism AI Labs, where we all work, we're currently hiring. We're hiring research engineers and Python engineers. So feel free to reach out to one of the presenters if you're interested, or click on the link provided here to see the latest open positions. We'd also like to extend our thanks to ECIR 2021, who allowed us to host this tutorial today. So very big thank you. It was great to be able to have such a great audience to present this tutorial to. And finally, feedback. We'd love for you to kind of fill out this very quick feedback form. If you have 2 minutes, I'll drop the link in the chat as well. So yeah, it would be great if you could put that in. It'll help us improve the tutorial. And so yeah, any feedback would be really, really, really greatly appreciated. So thank you all for your time. We have some time, that's it for today, but we of course have some time for some Q&A. So once again, feel free to drop anything in the chat or in the Q&A, and we'd be happy to answer. Thank you.